Hello students, good morning. How are you doing? How is your preparation? Tell me, did you revise the organic chemistry? Did you get time to revise it? I can see so many of you have joined. Keshav, Aizaz, Amaya, Chetan, Jia. Hello everyone, good morning. Okay, Amaya is saying she has revised 3 chapters. Very good. Here we will do all the organic chemistry. So basically it will not take that much time. I will finish it up. I will wrap it up quickly so that you can give a complete revision of the entire chemistry chapter, and again in the evening session a short live to wrap up everything. Okay. Okay, happy Women's Day to you as well. Thank you so much. Okay, thank you so much. Thank you to you as well. Happy Women's Day to all of the beautiful women who are watching me right now. So yeah, let's go ahead. So here again, organic chemistry, again the same agenda. We will be having all the chapter, all PYQs, model paper question, and your demanded 5 marker question. That also I will discuss over here. So don't worry, it will be sorted. Full organic chemistry and complete revision of chemistry will be done by today. So today around 6:37 I will leave you, and then I will ask you what about your confidence, and then again tomorrow morning I will come up. Okay, let's go ahead. Okay, so first we will start with the haloalkanes and haloarenes. Okay, so yeah, let's concentrate. Definitely I'm not going to discuss about the MCQ here, only the problems. Okay. Pradyur is saying 6 hours today. No, it's not 6 hours today because only organic. No, organic we are having haloalkanes, haloarenes, alcohols, phenols, aldehydes, amines and biomolecules. Okay, so even if you see the weightage wise, then also alcohol, phenol, then haloalkanes and aldehyde, these 3 are of heavy weightage. So these 3 we will do properly, and yes, aldehyde, ketone, sorry, biomolecules and amines also we will do. Most important questions and all that you can expect in your examination. Okay, so it will not take that much time, but yes, I will make sure that you learned the topic properly. Okay, so yeah, let's go ahead. So first is, these are quite common question for you people. Schwartz reaction. Okay, let me tell you the name reaction over here. In the haloalkanes, haloarenes chapter, they ask directly. Schwartz reaction, Finkelstein, okay, fatigue, Woods fatigue. Okay, these reaction they ask directly. So make sure you are writing the equation for them. Okay, so here you can see a little bit 1 or 2 line you can write, like any kind of alkyl fluoride are synthesized by heating the alkyl chloride or bromide with any kind of metallic fluoride, right? Silver fluoride, Hg2F2, COF2, this type of thing. If you just heat this, then you can go ahead. Okay, let me tell you one thing. If you know the name of the compound, see, this is easy, this is methyl bromide, right? Then only write it. If you are confident enough about the IUPAC name, then only you write below. If you are not confident enough, don't write it. You will get full marks. Okay, so in order to impress the examiner, don't ruin that particular person's mindset. Okay, so if you know the IUPAC name, then only you write, then only you go ahead. Okay, let's go. Okay, so explain Finkelstein reaction with example. As you can see, it's a very important for this here. You can expect, sorry, you can expect this question actually. Okay, so alkyl iodide we will prepare. Okay, so what we have to use? We have to use sodium iodide in acetone. Okay, so another one question can have, like we can have that why we used acetone for this case. Okay, why? Because you know NaCl and NaBr precipitation we are getting, that gets dissolved in acetone. As a result of this, if the product is removed by dissolving in acetone, then what happens? The reaction will proceed towards the forward direction more, right? It will proceed towards the forward direction more. So that is the reason why we use the acetone. Okay, let's go ahead. How do you prepare alkyl halide from alcohol? So here you can see alkyl halide if you are having, sorry, alcohol if you are having, let's say I am having CH3, CH2, OH, right? Now here simply you can give thionyl chloride, SOCl2. You can simply give thionyl chloride and you will end up with CH3, CH2, Cl. Okay, and as a byproduct, you know, you will end up with sulfur dioxide. Okay, so sulfur dioxide, that gas will be eliminated from the system, right? So as a result of this, purely this alkyl halide compound you will get. Okay, let's go ahead. Okay, so this question, a hydrocarbon do not react, just a minute. Okay, a hydrocarbon C5H10 do not react with Cl2 in dark, but react with sunlight to give you monochloro compound C5H9Cl. Identify the hydrocarbon. So how you are going to do this thing? So basically the general formula, what we know, general formula of any kind of hydrocarbon, that is basically CnH2n, and you know what, for this particular case this definitely is going to be a cyclic product because it will give you a monochloro derivative. Okay, so if I start from here, let's say if C5H10, right? So from here I am getting CnH2n, right? CnH2n, right? So from here I can see the option, it can be either alkene, okay, or it can be a cyclo compound. Two options are there. Okay, so now which one I will choose? I will choose like they are saying that it will not react the Cl2 in dark, okay, but alkene will react in dark, right? So definitely my compound is going to be a cyclo one. Okay, my compound is going to be a cyclo one. So definitely your compound is nothing but this. Okay, so for this particular case, all the hydrogen you can see these are equivalent. So further if you do the chlorination, you will get this type of thing, monochloro derivative. Okay, because all the hydrogens are equivalent for this case. Okay, just let me know if this thing is clear to you or not. Okay, again I have to explain, right? Fine. So just look at the formula C5H10. C5H10 if I write, it's going to be CnH2n type of molecule. So if you are having CnH2n type of molecule, what is this? This is definitely, it can be alkene or it can be a cyclo compound. Two options only. Alkene formula is CnH2n, right? And cyclo, that is also CnH2n. Now you can see they are saying that they do not react with Cl2 in dark. If it would be alkene, it would definitely react in the dark. Okay, vicinal dihalide compound it would make, but they are saying it will not react, right? So definitely alkene option is gone, right? Next, what is there? Now they are saying but it react in sunlight to give monochloro compound. Okay, so now definitely monochloro compound only for this particular case is possible because all the hydrogens are equivalent. But if you draw the alkene containing carbon 5, then you will get 2 degree alcohol, 2 degree carbocation as well. 2 degree, there you will get 2 degree alcohol, 2 degree chlorine as well. Okay, so for those cases you will get a different type of compound, different type of chlorine, alkyl chloride, right? But here only monochloro derivative you will get. Okay, so I guess this is clear. Let's go ahead. Okay, so yeah, this is the general formula CnH2n, and as you can see it does not react with the dark. Definitely it means that it's a cyclic structure. Okay, so monochloro compound means all the hydrogens are equivalent, so your structure is this. Okay, so let's go ahead. Give the preparation of aryl halide by Sandmeyer's reaction. Okay, so basically Sandmeyer's reaction, how I should start with? If I just start with the aniline, if I start with NH2 here, then what I have to give? I have to give HNO2, or you can write NaNO2 plus HCl as well, same thing only, 0 to 5 degrees Celsius. Here you will end up with benzene diazonium chloride, N2 plus Cl minus, right? So from here, what you have to give? You have to give Cu2Cl2 in HCl. Remember that here copper oxidation state must be +1. In Sandmeyer's reaction, copper's oxidation state is always +1. So you will end up with one benzene ring with one Cl. Okay, I guess this is clear to you. Let's go ahead. Okay, in haloarenes, para isomer, it's a very important question for this year. In haloarenes, para isomers have higher melting point as compared to their ortho and meta isomers. Okay, so isomers, why? Because para isomer, if you see, this para isomer is much more symmetric. Okay, that's why it can like fit itself in a crystal lattice in a much better way than that of the ortho and meta isomers. Okay, as a result of this, they have high melting point. As they can make the crystal more stable, they have high melting point. Okay, you can see this is the answer. You can go through it. The arrangement in the crystal is basically very much prominent. Okay, let's go ahead for the next question. Please, if you are having any doubt, please comment me here, and PDF definitely after the session you will get the PDF. I guess last day's PDF is also shared. I guess you got it. So yeah, let's go through. Okay, arrange the increasing order of boiling point. It is also a very important problem for this year. Okay, so first is dibromo, okay, bromomethane, bromoform, chloromethane, dibromomethane. Okay, so dibromomethane means the structure is going to be CH2Br2. Chloromethane is basically CH3Cl. Bromoform is basically CHBr3. And bromomethane is basically CH3Br. So definitely bromine is having the maximum atomic weight. So here 3 bromine is there in bromoform, so that will come first. After that 2 bromine, right? That is dibromomethane. After that bromomethane, then chloromethane. I guess this is clear to you. Let's go ahead. 1 chloropropane, isopropyl chloride, and 1 chlorobutane. So 1 chloropropane, again the structure you have to write, then only you will understand. So this is your 1 chloropropane, isopropyl chloride, this is your isopropyl chloride, this is your isopropyl chloride, right? So now next one is, sorry, this is directly attached. This is your isopropyl chloride. Next is 1 chlorobutane. Okay, so highest melting point definitely it's going to be for this, right? Boiling point, whatever. The highest boiling point is definitely is going to be this, because surface area is also greater. Okay, so 1 chlorobutane. After that, in accordance to the surface area, 1 chloropropane. Then isopropyl, we have the branching. Hence, isopropyl chloride will come later. Okay, I guess this particular thing is clear, and please make sure this particular question is very important and you are going through it properly, you are understanding it properly. Okay, let's go ahead. Okay, so the most expected, I mean not expected, rather better to say the most wanted thing that you people kept asking for, that ma'am 5 marker organic compound, 5 marker organic question, sorry, 5 marker organic question. So this is a 5 marker organic question that you can expect in part D. So in this case also you can get part marking. If you see, so many things you have to find out, A, B, C, D, you have to write the equation, so many things you have to do, right? So part marking you can get out of it. And again let me tell you, if you are not confident enough to deal with this type of problem, leave that. Okay, I always suggest, whenever you will see that there are options, right? If you feel that you are not confident enough, go through once. If you are not confident enough, leave that. Okay, so you can see primary alkyl halide C4H9Br reacted with alcoholic KOH. So what we will do, we will just make a scheme and we will keep doing it. Primary alkyl halide C4H9Br. So I am starting with C4H9Br. Okay, reacted with alcoholic KOH. Reacted with alcoholic KOH. Okay, so these will undergo beta elimination or dehydrohalogenation, right? Give you compound B, right? Compound B is reacted with HBr. It is reacting further with HBr to give you compound C. This C and A, this is my A, right? So now this C and A, they are isomers. Means in C also, I will get 4 carbon system. It's a 4 carbon system. It's a 4 carbon system, right? Okay, next you can see now which is an isomer of A. Okay, fine. When A is reacted with sodium metal, it gives compound D. So A is reacting with sodium metal, it is giving a compound D. Okay, so D formula is basically, just excuse me for a minute. Okay, sorry for the inconvenience. You can see when A is reacting with sodium metal, it is giving a compound D. D is having the formula C8H18, right, which is different from the compound formed when N-butyl bromide is reacted with sodium. Fine, means A cannot be N-butyl bromide. Right, A cannot be N-butyl bromide. So what are other possibilities? So if A is not N-butyl bromide, so definitely A must be isopropyl bromide, right? If it is not N-butyl bromide, then it must be isopropyl bromide. Now let's begin with the isopropyl bromide. See, if I start this with the isopropyl bromide compound, what is the formula? Isopropyl nahi, butyl, isobutyl bromide, okay? 4 carbon system. So CH2, here also I am having CH. This is the formula of isobutyl, then bromide. Okay, this is the formula of isobutyl bromide. Okay, so let's go ahead. Isobutyl bromide, it will undergo alcoholic KOH, means beta elimination, right? So beta elimination means here the double bond will come, hence you will end up with something like C double bond CH2, here I am having CH3, so beta elimination. Then you are giving it HBr means I am doing Markovnikov, right? I am doing Markovnikov. So let's do Markovnikov. So once you are doing Markovnikov, you will end with, here in this carbon I will get the bromine, right? So CH3, here CH3, here itself you will get the bromine, here you will end up with CH3. So now you check, this is your A, this is your B, this is your C. A and C, they are isomers to each other. That is also correct. Okay. Now what we will do, A we will treat with sodium. Okay. So if it is treated with sodium, so Wood's reaction is going to take place. So to this unit will be attached. So C, just let me write it like that, CH3 whole twice. CH3 whole twice, CH, CH2, then another CH2, CH, CH3 whole twice. Okay, so this is basically the C8H18 compound. This is your basically D. So yes, if you can do, if you are confident enough to do the entire thing, then only go ahead for this. So all the reaction also I wrote and the product also. Okay, just let me know if you understood this thing or not. Okay, very good, Pradyun. So I guess this is clear to you. So this question is important actually because this was given in your model paper. So make sure that you are practicing this type of thing, okay? At least one or two, whatever is given in the model paper, that you make sure you are practicing. Okay, so yeah, let's go ahead. So this is a 5 marker problem. Okay, always I suggest you go for those questions where the marks distribution is something like 2 plus 2 plus 1 or 3 plus 2. Those are like more convenient to get marks. Okay, let's go ahead. Okay, so what is this? Anyway, write the steps involved in SN1 mechanism for the conversion of tertiary butyl chloride to tertiary butyl alcohol. So this is again very important. SN1 and SN2, both the mechanism you should practice because you can get any one of them. Directly they may not ask that write SN1, show SN1 mechanism, or like they can ask you like conversion of tertiary butyl chloride to tertiary butyl alcohol. Let me show you. This is your tertiary butyl compound, right? This is your tertiary butyl. You have to start with chloride, right? So first step is basically formation of carbocation. So what will happen here? No reagent, nothing is needed. So CH3, CH3, CH3. Here you will get the carbocation. So first step is basically slow, and this is only called a rate determining step. So rate determining step, how I should write the rate law? Rate equals to K into reactant. Reactant is tertiary butyl chloride, right? No other thing is there, so that's why power 1. Okay, it's a first order reaction, substitution of nucleophilic reaction in first order. Okay, so I guess this is clear because in the rate determining step no other things are needed. Now further in the second step, this thing will be used. CH3, 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 right? Carbocation. Now you are having, let's say, OH minus as a nucleophile. Right? What you can give, what reagent you can give out of it? Aqueous NaOH, aqueous KOH, this type of reagent you can give. So it will attack over here, okay, and you will end up with the tertiary butyl alcohol. Right? So this is basically the nucleophilic attack. Okay, so this is the carbocation intermediate. Make sure you are writing that below. Okay, and one more thing that I must tell here, that is the same side from where the leaving group left, the OH minus also enters. Okay, the same side where the leaving group lives, in the same side the OH minus enters. Okay, as a result of this, if you start with a chiral carbon, or asymmetric compound or optically active compound, then you will end up with the racemic mixture. Okay, so what is racemic mixture? Racemic mixture is basically the equimolar mixture of R and S, equimolar mixture of two enantiomers. Okay, so remember what is racemic mixture? Equimolar mixture of two optical isomer. I am just writing R and S. Okay, this is sometimes called racemic modification as well. This is sometimes called as racemic modification. Remember this. Okay, let's go ahead. So this is the thing. Again, it is written clearly. You can see here. Okay. So yeah, let's go ahead. I guess there is no doubt in SN1, SN2 reaction. Sorry, this is SN1. I guess there is no doubt in SN1 reaction. I told you even for the chiral carbon what you can end up with. Let's go ahead. Write the steps involved in SN2 mechanism for the conversion of chloromethane to methanol. Okay, so I have to start with chloromethane. So you are having CH3Cl. Right? So SN2 mechanism is basically a single step concerted mechanism. Single step concerted mechanism that proceeds through a penta-coordinated transition state. What I said? Penta-coordinated transition state, mention that below. Okay. So here you can see first step. If you go for the first step, then what happens basically? OH minus nucleophile. See, in the first step itself the nucleophile attacks. Okay. So nucleophile attacks from the back side. Okay, nucleophile attacks from the back side. Okay, let me show you with all hydrogen splitted, then it will be easier for you to understand. Okay, so OH minus will attack from the back side. Okay, so now here you can see, here I will end up with a penta-coordinated transition state. You should draw it like this. Here you will be having one hydrogen. This leaving group is about to leave the system and this nucleophile is about to enter the bond, about to make the bond with the carbon. Okay, here one hydrogen, here one hydrogen. Amazingly, carbon exists with a valency 5, you can see here. Okay, so now here the charge is half lambda negative, delta negative, sorry. Here also half delta negative and this is delta positive. Right? Half, why I am writing? Because it is a partial bond, not a full bond. So what is this? This is basically a penta-coordinated transition state. We studied about the activated complex, right? So this is basically the activated complex. Okay, so here you can see if I want to write the rate. Okay, so I have only one step. Okay, so this rate itself, it involves both the reactant and attacking reagent. So K into CH3Cl power 1 and OH minus also power 1. So 1 plus 1, 2. So that's the reason your this substitution of nucleophilic reaction becomes of order 2. Okay, so further from this penta-coordinated transition state, what happens? This chlorine leaves, right? As a result of this, you will see this compound CH, here you will have OH, here hydrogen, here hydrogen. Okay, so from the side where the Cl leaves, from the opposite side OH attacks. Okay, as a result of this, the upcoming structure becomes a little bit tilted. Okay, if you see the 3D geometry, it becomes a little bit tilted. So definitely, if you start with a chiral carbon, if you go for a SN2 reaction, you will end up with inversion in configuration. Okay, means if you are starting with R, you will end up with S. This is called inversion in configuration. Okay, I guess this is clear to you. Okay, let me check. Ma'am, while purchasing test series, okay, test series we will talk later. Ma'am, while reacting with alcoholic KOH, I took the compound as bromobutane and then after reacting it with but1ene, then with reacting with HBr, it will form isopropyl. Then I reacted with sodium. No, sodium last case, right? Let me go back once. No, here I will not react with sodium. Here no. See, with A you have to react with sodium, not here. Okay, so it is a hint about A. You can see when A is reacted with sodium metal, it gives compound D. Okay, A is reacting with sodium metal, not that C. Okay, I guess this is clear to you. Okay, let's go ahead. Okay, distortion is asking why do we need to take isobutyl bromide. Isobutyl bromide we have to take because that is also a hint given. See, N-butyl bromide, okay, N-butyl bromide if you start with, okay, then N-butyl bromide means this. This is your N-butyl bromide, okay. So they are saying that this C8H18 compound, this C8H18 compound does not look similar when this particular compound will make the reaction. So if this particular compound react, then you will get C8 system. All the carbon attached in a chain 1, 2, 3, 4, 5, 6, 7, 8. This is not D. That's what they are saying, but they are isomers. If you start with normal this structure, you will end up with this, but they are saying this is not D. So definitely I don't have any other choice. If this is not the option, so definitely it must be isobutyl. Definitely one branch is there. Other no option is there to draw this. Think about it. You have butyl bromide, right? Either you can do this in a chain or you can keep it one branch. That is only the isobutyl. That's why I have taken isobutyl. This is the hint. Okay. Okay, I guess this is clear to you. Let's go back. Okay, we were discussing about this thing. Okay, let me take, someone is saying a protic solvent. Let me just give an idea about it. So for SN1 reaction, you can see it is proceeding towards, proceeding through a carbocation intermediate. Okay, carbocation is a charged species. Okay, the charged species needs something in its surrounding that is having some dipole moment. Okay, so that's the reason I need polar solvent. Polar solvent means it has dipole moment. So dipole moment can stabilize the carbocation. If the carbocation gets stabilized, SN1 reaction will be faster. So that's the reason I need polar protic solvent here. Polar protic solvent. Majorly polar solvent. Protic means it's a proton donor. That's it. Okay, next for this case, you can see this is a dipole compound, right? This is also a dipolar compound, right? We will be having dipole moment. So now in order to make it dissolved, okay, like we know the concept like dissolved like, right? In order to make this particular compound dissolved, we need a polar solvent. Okay, so polar solvent can stabilize this particular process. Okay, because all the step you can see dipole moment you will get. So that's the reason I need polar solvent here. I guess this is clear. Let's go ahead. So yeah, this is the mechanism, concerted way. You can mention this with respect to this flying wedge representation. That is also cool. Let's go ahead. Haloalkanes react with KCN to form alkyl cyanide and with AgCN to form isocyanide. Why? A little bit this discussion we did synergic bond actually. Okay, so basically what happens, KCN is highly ionic. So KCN, whenever you are just dissolving, it will dissociate in K plus Cn minus. But in case of AgCN, silver and carbon bond, they are highly covalent, right? So carbon end is not free for the donation, nitrogen end is free. Okay, so that's the reason from the nitrogen end, when it donates the electron, it becomes cyanide, isocyanide. Okay, NC. Okay, I guess this is clear. Let's go ahead. substitution reaction occurs slowly in haloarenes compared to benzene? Give reason. Very important question, okay? It's a very important question. Let's go ahead. So basically, first of all, minus I effect of halogen atom. Okay, so minus I effect of halogen atom, because these haloarenes, they have some tendency to withdraw the electron from the benzene ring. Okay, so if let's say I am having this compound, if this chlorine is withdrawing the electron density of the benzene ring, so benzene ring becomes electronically deficient. It becomes electronically deficient, right? So now as a result of this, electrophilic substitution occurs slowly. Electrophilic means what? Electrophile needs electron and benzene becomes electronically deficient. Not completely, little bit. So definitely whenever electron, they need electron, electrophilic. So that electrophile is coming to react. Definitely it will occur slowly. Right? I guess this is clear. Yes, ring get deactivated. True. Next, as a result, the ring gets deactivated as compared to benzene and hence electrophilic substitution occurs slowly. I guess no doubt here. Aryl halides are less reactive towards nucleophilic substitution. Why? So you can see first one is the resonance effect and next one is the sp2 hybridization. Very, very important question for this year. Okay, so resonance effect, why? Because of the resonance, this carbon and chlorine bond or carbon and halogen, whatever the halogen you are using, here see this particular thing will come here, this will go, like that the resonance will take place, right? So carbon and halogen will be having a partial double bond character, right? So it's difficult to be substituted. Okay, next one is sp2 hybridization of carbon. sp2 means more s character and as a result of this the bonds are like hold very strongly. Okay, let's go ahead. I guess it is clear. Very good, Amaya. Let's go ahead. Okay, explain Fittig's reaction, Wood's Fittig and Fittig. Okay, so one by one you can see you already know about it. So this particular reaction, here you are having one aryl halide compound in presence of sodium, dry ether. This is basically your Fittig reaction. Okay, this particular thing is your Wood's Fittig, right? One aryl halide, one alkyl halide. This is your Wood's Fittig. Okay, next, water Grignard reagent, write its general formula. So in case I am going fast, if you feel any doubt, please comment me here so that I can understand. Due to conjugation, conjugation in what? Conjugation, where you will get conjugation? No, here conjugation, definitely resonance, better to say resonance. Benzene ring is there, say resonance. Okay, definitely resonance, conjugation is one of the thing that happened during the resonance. So yeah, okay, let's go. Okay, water Grignard reagent, write its general formula. I guess you know this, it's a organomagnesium halides compound. Okay, they are called Grignard reagent. Okay, so how we represent this? RMGX. RMGX. This is how we represent it. Okay, let's go ahead. What are freons? Very important question, okay, from the polyhalogen compound. What are freons? Name the poisonous gas evolved when Cl2 is oxidized by what? Air. So chlorofluorocarbon compounds of the methane, they are collectively known as freon. Okay, and Cl2, the poisonous gas, whenever Cl2 will be oxidized, that is basically COCl2, that is phosgene, right? That is phosgene. Okay, let's go ahead. It is also a very important problem for this year. Chloroform is stored in closed dark colored bottles. Why? Because they will oxidize to phosgene. Okay, so it is slowly oxidized by air in the presence of light to give you the poisonous gas phosgene. Okay, I guess this is clear to you. Let's go ahead. Okay, wait. So these products I already wrote, I guess. Anyway, complete the following reaction. So for this case, the first reaction, if you just look at, this is basically your Markovnikov rule, right? This is basically your Markovnikov rule. So for the Markovnikov rule, this position carbocation will be stabilized, and hence bromine will be attached here and hydrogen will be attached here. Okay. So now from some compound you got this. Okay. So definitely it came out from the Fittig reaction. Okay. Sorry, Woods reaction. It came out from the Woods reaction. So from where you should start? The starting material, just make one cleavage here. Okay, just break the bond from here. Okay, so you will get 2 carbon, means you have to start with 2 unit of ethane. You have to start with 2 unit of ethane. Okay, next one here, important question, hydrolysis of aryl halide, aryl chloride, okay, or chlorobenzene, hydrolysis of chlorobenzene. In presence of NaOH, you will end up with phenol. You will end up with phenol. Okay, explain Sedzev rule with an example, very important. Okay, explain Sedzev rule with example. Let me show you one example. So basically, I can take this type of system. Okay, just hydrogen I split it so that you understood. Okay, so let's go ahead. Let's go ahead with example how you should explain. So this hydrogen can jump and this bromine can leave. As a result of this, I will end up with something like this: CH3, CH2, CH, double bond, CH, CH3. Now one more option is there. One more option is this hydrogen can jump and this bromine can leave. So as a result of this, I will end up with CH3, CH2, CH2, CH, double bond, CH2. This thing. Okay. Now the question is, I can get both of them, but which one I will get as a major one? So I will get this particular thing as a major one. Why? Because the alkene that I am getting is more substituted. So what is this? I am getting more substituted alkene. More substituted alkene. So whenever dehydrohalogenation is taking place, at that time more substituted alkene will be the major product. That is your Sedzev rule. Okay, very good, Pradyun. Okay, I guess this is clear to you. There is no doubt. So whenever they are asking, explain with example, please make sure you are showing the entire thing. This will be minor. Why? This is less substituted. Like that you have to mention. Okay, I guess this is clear. Let's go ahead. This is the rule is given here already. Okay, so okay, write any 3 differences between SN1 and SN2 reaction mechanism. I guess this one. Okay, this, I guess it is clear to I guess you can see this. Let me check once. Yeah, it's visible to you, I guess. Okay, so one follow first order reaction, another follow second order reaction. Okay, not understanding. Nagabhushan, can you please tell me what you did not understand so that I can repeat that? Anyway, by that time you just tell me this particular thing. I'm not explaining again. You can take any 2 or 3 point out of this and you can go ahead. Okay, carbocation reactivity, order of reactivity of alkyl halide, that you can go through. Okay, 3 degree, 2 degree, 1 degree, because it proceeds through carbocation intermediate. Okay, so yeah. Next question, identify A and B. So very common, A is going to be what? A is going to be, this is your diazonium like this is the reagent to form the diazonium chloride, right? So you will end up with diazonium chloride, N2 plus Cl minus, right? Now if you want to like get Br out of it, so what you have to give? 2 Sandmeyer's reaction, Cu2Br2 give HBr in presence of HBr. Okay, I guess it is clear. Yeah, very good. Let's go ahead. Okay, so write the mechanism involved in the conversion of 2-bromo 2-methyl propane to 2-methyl propan 2-ol. Okay, so I am having 2-bromo 2-methyl propane. So propane is basically, just a minute. This is your propane, this is your bromine. Okay, 2-bromo 2-methyl. So which reaction is this? So directly they may not tell you. They can tell you that like this, 2-bromo 2-methyl propane to, again this thing, CH3, 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 here OH, right? 2-methyl propan 2-ol, right? So this is nothing but your SN1 mechanism, right? So I am not repeating this, we already discussed the mechanism, entire mechanism. Okay, so I guess this is clear for you. Next, what are enantiomers? Name one physical property which differs in enantiomer. Okay, so these enantiomers are basically pair of chiral molecules that are non-superimposable mirror image. Okay, and what differs? The optical activity. Okay, let's go ahead. Write the equation. This is a 5-marker question, you can see, but part question you will get. Okay, so first write the equation for the steps involved in SN1 mechanism. Again, I am not repeating. Hydrolysis of 2-bromo 2-methyl propane. Hydrolysis means you have to treat this with OH, right? Next, name the product formed for the reaction of isopropyl iodide on alcoholic KOH. Okay, let's go ahead. So basically isopropyl iodide, if you are having, this is your isopropyl iodide, sorry. Okay, this is your isopropyl iodide. Okay, now you have to treat this with alcoholic KOH. What it will undergo? It will undergo beta elimination, dehydrohalogenation. So let's do it properly. Okay, so I am having CH3, C, here I am having I, here I am having CH3. Okay, so if like that I can write CH2 here, CH2 here, here hydrogen, right? So it will jump here, it will be removed. Okay, so as a result of this I will end up with something like this, CH2 double bond CH CH3. Okay, this is the product. What is a condition to be satisfied for a compound to be chiral? So this particular compound, this particular carbon must have all different groups, let's say A, B, C, D, different group in its 4 valency. Another is no symmetry element should be there. No symmetry element should be there. Okay, these are the 2 conditions. I guess this is clear. Okay, Amaya is saying propene. Very good. Let's go ahead. Okay, what is a racemic mixture? Equimolar mixture is equimolar mixture of D and L, dextrorotatory and levorotatory isomers. I guess clear. Let's see. So we are we just finished this chapter. I guess this is not clear properly. No. Wait. No, I can't zoom it. Okay, few definition that you have to study. First is, let me write it for you, retention. The definition that you have to study, that is retention, inversion, stereocenter, okay. Next is enantiomer, okay, and racemic mixture. These are the sets of definition that you must go through for this, okay. So next, name reaction that you have to go through: Swartz, Finkelstein, Friedel-Crafts, Woods, Fittig, and Sandmeyer. These are the name reactions. So you will get the PDF there, it will be clear, I guess. Mechanism, SN1 and SN2. So these are the important thing from where you will get. So whatever the important question that we covered from the haloalkanes and haloarenes. Okay, I guess this is clear for you. Let's go ahead. Question 3a. What was question 3a? Write the mechanism involved in conversion of. This is SN1 mechanism, Baba. That's what we did, na? That's what we did. So what you have to do here first? First you have to, from here, first the carbocation formation. So C with CH3 whole thrice carbocation, right? So from this carbocation, if you treat this with OH minus, then you will end up with CH3 whole thrice OH. That's it. That's it. SN1 mechanism. I guess it is clear. I will skip CH8. What is CH8? I don't know. If you feel like those type of 5-marker question is hectic for you, you can skip them. So can we start alcohol phenol? Yes? Okay, Jia, very good. Can we start now? Alcohol, phenols and ethers? Yeah? Okay, 5 minutes break. Chalo, koi na, 5 minutes break. 5 minutes, nahi, 3 to 4 minutes actually. I will have some water, you also have some water and come back, okay? So I can see so many of you like initially joined and then left and all. I can see the voting of you as well, but you people are not feeling that you should like the session. Why this is? Okay, don't you think that I deserve a small thumbs up from you people? You people are not liking the session and that's really demotivating. What is CH8? I don't know. Just can you please explain what is CH8? Okay, distortion, thank you. Provoker, thank you. Krishav, thank you. Okay, chapter 8. Okay, what is chapter 8? Which one? Aldehyde, ketones and no, it's a very bad choice actually. Don't don't skip that chapter. It's a very heavy-weighted chapter in the organic chemistry. So I don't suggest that you should actually leave the chapter of aldehyde ketone. At least 3 chapters you should be prepared well in the organic chemistry: haloalkanes, alcohols and aldehydes. I will be also focusing on them. Anyway, if you are feeling that you are not comfortable, again I am telling you, don't study anything new. So whenever I will do the questions, okay, check the questions only. Okay, check the name reaction that I will do, that will be enough. Okay. Okay, thank you for showing your love. See, whenever I just told you it was something 27 or something, now it become 51. So many people just now liked. Okay, so please make sure you are liking the session because it motivates me a lot to stand here for you people. Okay. From this chapter means alcohol phenols, I guess it was 10 in accordance to the blueprint. 10 or 12, something like that. If you follow the blueprint, you will get it. Okay, so let's go ahead. Okay, 5 minutes over. Let's start. Okay, so yeah, it is 10 marks. That's what I told. It is 10 marker question you will get. Okay, so I guess it is clear. No, beta. Actually, that video that I made, those are taken from the question bank, model paper, analyzing the previous year question, everything. So, video, whatever the thing you have studied, those things also, I guess all the MCQs are been uploaded as well. Okay, please go through them. It will be more than enough. Okay, now at this moment, don't go back further for the MCQ. Okay. So once you are done with the discussion, once you are done with the preparation of MCQ, keep it aside. Okay, don't mess up everything together. Okay, let's go. Okay, see here one MCQ I have kept because it involves a lot of concept here. Okay, so that's why I feel like this particular question, once I discuss, then I will go ahead. Okay, so see, the question is basically, just a minute. Okay, let's go. Propene is allowed to react with HBr in presence of benzoyl peroxide and the product is subsequently heated with aqueous KOH, the final product. Okay, so I'm having propene. Propene means my structure is something CH3 CH double bond CH2. Okay, so if I treat this with HBr in presence of peroxide, so in presence of peroxide it will undergo anti-Markovnikov, right? It is basically anti-Markovnikov. Okay, so definitely I will attach the bromine here in the terminal carbon where there are more number of hydrogen, right? So CH, here I will be having hydrogen and here I will be attaching the bromine, right? So now further what you have to do, further this product will be heated with KOH, aqueous KOH. Be careful if they are saying aqueous KOH or they are saying alcoholic KOH. Alcoholic KOH will give you beta elimination, aqueous KOH will give you substitution product, means Br will be substituted with OH. Right, so we will end up with simply CH3, CH2, CH2, OH. That's it. Okay, so now what you have to do? You have to check for the name. 1, 2, 3. Okay, so 1-propanol. Option C is the correct one. I guess this is clear to you people because as you can see it has so many steps involved and then the IUPAC nomenclature as well. I felt I should keep it. Okay, let's go ahead. Okay, very good. So many of you. Okay, you did this before. Very good. Let's go ahead. This is one more question that is also very much important. I guess in the MCQ session I did or I haven't done, I forgot. But because of the conceptual revision, I kept them. Okay, so this is basically you have ether and you have to treat this with HI. So this type of one problem definitely you can get in your upcoming tomorrow's examinations or upcoming tomorrow's examination. Okay, so let's go ahead. In case, so definitely here the bond cleavage will be there, right? So let's see. What is the compound? C6H5, right? Let me draw it like this. C6H5 along with O, then CH2, then again C6H5. Now the problem is, now the question is, where I will get the I and where I will get the alcohol. Okay, so basically here I will break the bond, and here I will add the iodine, and here with the oxygen I will end up with the benzylic alcohol. So you will get this plus OH CH2 this. Okay, so your answer is going to be which one? Option A. So your answer is going to be option, wait, I only did wrong, wait. Once you are doing the phenol, that must be resonance stabilized, right? So this is your CH2, here's oxygen, like this. Okay, so now if you add the HI out of it, so basically here you will end up with the cleavage, and you will end up with phenol, okay, and you will end up with ICH2, then this. Okay, so this phenol is basically resonance stabilized. So your answer is basically option C. Okay, so I guess this is clear to you. Okay, I guess this is clear to you. Let's go ahead. Okay, you are not understanding where you should put hydrogen and where you should put the I, right? So basically you have to check if the phenol is forming, if or alcohol is forming, if there are any possibility to stabilize it. Like that, initially what I did, I initially put it opposite side, but then then it came to my mind, okay, it is benzylic alcohol, there is no stabilizing factor, right? But if I put the hydrogen here, then what is happening basically? Then this is getting resonance stabilized, right? As a result of this, I will get the major product, phenol. Okay, so I guess it is okay. I guess this is fine. Let's go ahead. Amaya, just let me know if you understood or not. Okay. Okay, fine. Next, here you can see, here you are having the alcohols, right? Here you are having the alcohols. Now this is the entire preparation of alcohols. I just kept it in one slide. So now from the alcohols to acid, ester, if you want to come, from the acid or ester, if you want to come back to alcohol, you can just treat this with lithium aluminium hydride or hydrogen in presence of palladium. From Grignard reagent, if you want to come back to alcohol, you have to treat it with aldehyde. Okay, from alkenes to alcohol, H plus and H2O, hydrolysis, okay, or hydroboration oxidation you can do. Okay, oxymercuration, demercuration you can do. Okay, next, if you are having aldehydes ketone, then again do the reduction with the NaBH4 or hydrogen in presence of palladium. Okay, so I guess it is clear. Let's go ahead. This is the preparation, just overall thing. Okay, let's go. Okay, write the product for the following. So first case is, this case is basically hydrolysis. So hydrolysis, just remember few things. Here also OH will be added, here also OH will be added, but the position matters. Okay, why the position matters? Because for this case it will follow carbocation intermediate. So you have to check in which carbon the carbocation will be stabilized. So basically if you check in this particular carbon, if the carbocation is formed, then it will be 2 degree carbocation, a little bit more stable. So as a result of this, you will end up with this thing, CH, here OH, here CH3. Okay, so you will end up with OH in the middle carbon. Okay, but here B2H6H2O2, you will always end up with the terminal alcohol. Okay, so anti-Markovnikov rule. Okay, CH3, CH, CH2 basically, CH2OH. Okay, so this will follow Markovnikov. B2H6 means hydroboration oxidation will always follow anti-Markovnikov. Okay, I guess this is clear. Let's go ahead. Okay, what is hydroboration oxidation reaction? Give an example. Okay, so this is a little bit, theory, not needed if you can write the reaction. So basically this is the reaction. I guess it is visible to you. Yeah, this is visible. Okay, here you can see this, you are having one alkene unit. So alkene will react with boron and hydrogen bond. Okay, one hydrogen, see if I just write it here, it will be clear for you to understand. So hydrogen B and other hydrogen is also there, like that. Okay, so this B will go here and this hydrogen will go here, like this. So hydrogen, and here you will be having BH2, right? So now this boron is having more boron hydrogen bond. See, more bonds are there, right? BH2, two more bonds are there. So those bonds will be also replaced. Okay, let me just show you once. Sorry. Let's say I am having this thing, CH3, CH double bond, CH2, right? Now hydrogen, B, hydrogen, hydrogen. So this will go here, this will go here. Fine. As a result of this, you will end up with something like CH3, CH, here hydrogen, here single bond, CH2, here I am having B, another hydrogen bond, another hydrogen bond. Now what will happen? Again I am having another alkene, let's say. Let me write it like that. CH3, CH double bond, CH2. Okay, then what will happen? This particular hydrogen will go here, this boron will go here. Okay, as a result of this, you will end up with something like this. CH3, CH2, CH2, here B, one hydrogen, here also CH2, CH2, CH3. One more B hydrogen bond is there, again it will be reacting and you will end up with CH3, CH2, 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 B, CH2, CH2, CH3, and here also again the same thing, CH2, CH2, CH3. Okay, you will end up with this. Okay, so that's what it was given there in a single step. Okay, this thing. Okay, so further if you do hydrolysis, then you will end up with the alcohol at the terminal position, you will end up with the boric acid as well. Okay, BOH whole 3. I guess this is clear to you. Let's go ahead. Okay, I guess you understood this. Okay, chalo, let's go ahead. Give two methods to prepare alcohols from carbonyl compound. Okay, so already we did this in that one diagram I showed you. So lithium aluminium hydride, you can treat this, okay, or platinum palladium, okay, in presence of that hydrogenation you can go ahead. Okay, so next question you can see how to prepare alcohols commercially from carboxylic acid, that is basically through hydrolysis of ester, you can see. Okay, so ester undergo reduction. Okay, so ester, if it breaks down, how the ester is formed? By the reaction of alcohol and carboxylic acid. Now if the ester if it breaks down again, then you will get back your alcohol and the carboxylic acid. Okay, so this is the reaction. See here, this is your carboxylic acid. In presence of alcohol, you will get the ester. This particular ester, if you just do the reduction, you will get back the alcohol and the particular alcohol from where you started. Okay, so this is how you should do the reduction of the ester. Okay, let's go ahead. How to prepare 1 degree, 2 degree and 3 degree alcohols from Grignard reagent, give equation. So this is a very important problem for you. So for this case, write the equation as well. So I will show you the equation here. Only it is written as by treating it with aldehyde and Grignard reagent, but I am showing you the reaction. Wait. First we will prepare the 1 degree. We will prepare the 1 degree, right? So for this case, what I have to start from aldehyde. Okay, now I am having CH3 MgBr, let it be CH3 MgBr. Okay, so this CH3 will attack here, this bond will open up, and as a result of this, it will end up with HC OMgBr, here again hydrogen, and here you will end up with CH3. So further H3O plus you treat, H3O plus if you treat, you will end up with 1 degree alcohol. HC, here OH, here hydrogen, here CH3. Okay, this is your 1 degree alcohol, right? Let's go ahead with the 2 degree alcohol. Okay, so this is the reaction that you have to draw over there. Let's go ahead with the 2 degree. So what we can react any other aldehyde. So let's take acetaldehyde. Okay, so CH3 COH. Okay, so here I will treat this with CH3 MgBr. CH3 MgBr. Okay, so this will attack here, this bond will open up. As a result of this, you will end up with something like CH3 COMgBr. OMgBr. Here you will get CH3, here you will get hydrogen. Okay, further if you do the hydrolysis, H3O plus, then this will be OH, this will be OH, this will be CH3, this will be CH3, and here you will end up with hydrogen. That's it. It is a 2 degree alcohol, right? Let's see 3 degree alcohol. 3 degree alcohol, you have to start with you have to take ketone. Okay, so ketone, if I take, let's say acetone, CH3 C double bond O CH3. Okay, if I am having CH3 MgBr, if I am having CH3 MgBr, this CH3 will attack here, this will open up. Okay, as a result of this, you will end up with CH3 C, here you will be having OH. Here only I am treating it with H3O plus, second step. Okay, and here you will be having another CH3, here CH3. This is your 3 degree alcohol. Okay, what happened? Just a minute. Okay, sorry for the inconvenience. I guess this particular thing is clear to you. Just let me know if it is clear. 1 degree, 2 degree and 3 degree alcohol. Okay, let's go ahead. Fine, let's go ahead. Okay, again one important problem. Just a minute. boiling points of alcohols are higher than other classes of organic compounds like hydrocarbon, ethers, haloalkanes of comparable molecular mass. Give the reason. So the reason is basically nothing but they can form the hydrogen bond with the water. Okay, and again the second question, you can see alcohols are soluble in water. Why? It is just because alcohols can form hydrogen bond with water. Okay, so here comes the reason. Let's go ahead. This is the cleavage of oxygen and hydrogen bond, the reaction of alcohols. Okay, so here you can see you can react it with R prime COCl, you can react with the acetic anhydride type of compound or any kind of anhydride, you can react with the sodium, that will tell about the acidic nature. Okay, you can react with the carboxylic acid, that will end up with the ester. Okay, this is the overall reaction. So let's go ahead with the problems. Okay, what is the effect of electron donating substituents on acidity of alcohols? Alcohols are weaker acid than water. Give reason. Very important question, very very important. Okay, so if you are having electron donating group, let's say I am having phenol. Okay, I am having here what? OH. Okay, here I am having electron donating substituent like NH2. This NH2 is basically electron donating group. Okay, so basically this NH2 will give supply of electron and this oxygen will get the enough supply of electron and oxygen hydrogen bond will not break. Hence, electron donating, in presence of electron donating group, acidity of alcohol will decreased. Okay. Next question, you can see alcohols are weaker acid than that of the water, because if you write the alcohol, let's say I am taking C2H5OH, okay, and I am taking H2O. Okay, so here I am having a plus I effect having group. A plus I effect having group that can push the electron towards oxygen. So if, because it is an electron donating group, right? So electron donating group always reduces the acidity. Okay, but in water I am not having any kind of electron donating group, hence water is more acidic than that of the alcohol. No, hydrogen bonding is not related to the acidity. Hydrogen bonding is not related to the acidity. It is basically here I am having electron donating group, here I am having no. See, this bond can be broken easily because nothing is there to pull the electron, right? So here you can see electron donating group is giving electron, right, to oxygen, enough electron supply. Then why oxygen hydrogen bond will break? Oh, okay, before question, fine. I guess this is clear for you. Let's go ahead. This is the reason. I guess just go ahead. I guess you will understand. Okay, next question. What is esterification reaction? Give an example. Next, what happens when ethanoic acid reacts with methanol in presence of H2SO4? Esterification takes place. Same question only. Okay, so you can see esters forms. Okay, wait, let me show you the reaction. Ethanoic acid reacts with methanol. CH3 COOH, right? Okay, let me break down the structure. C double bond OH, right? Plus I am having methanol, hydrogen, oxygen, here CH3. In presence of catalytic amount of acid, okay, they will form the ester. Okay, CH3 COO CH3. Okay, so this hydrogen and this OH will go off. Okay, in the form of water. Elimination of 1 unit of water. Okay, I guess this is clear to you. Doubt in previous question? Okay, tell me what is the doubt? So here basically let me just explain once again. Electron donating group, if you are having, Okay, electron donating group will increase the electron density on oxygen, so oxygen will not leave hydrogen easily. Okay, as a result of this, acidity decreases. Okay, acidity, when acidity arises because of the presence of H plus. Now H plus is not itself is coming, then why acidic? It's not acidic anymore, right? So, and ethanol and water, if you compare, ethanol is having that C2H5, that is a plus I effect having group. So plus I effect, what it is, basically electron pushing. It pushes the electron towards the oxygen. So oxygen becomes more electronegative. So why it will release hydrogen so easily, right? It will not release. As a result of this, water becomes more acidic. I guess it's clear. Let's go ahead. Okay, so this is the cleavage of CO bond, means this bond. Okay, if you cleave this particular bond, then this type of reaction you can expect. All of them are very important. First is dehydration. It is very important, Lucas reagent, and in presence of PCl5, I mean PCl3, this type of thing. Okay, let's go ahead. Okay, what is Lucas reagent? Again, you know, super important question. How would you distinguish between 1 degree, 2 degree and 3 degree alcohol by Lucas reagent? So, Lucas reagent is a mixture of ZnCl2, sorry, you can take it as concentrated HCl. Okay, it's called Lucas reagent. Let's go ahead. So what basically happens, Lucas reagent, it gives quick turbidity whenever it will react with the 3 degree alcohol. Okay, it will give you quick turbidity whenever it will react with the 3 degree alcohol, and it will give turbidity after 3 to 5 minutes whenever it will react with tertiary alcohol. Tertiary means 3 degree. 3 degree alcohol, quick turbidity they will give, and in 2 degree they will take 3 to 5 minutes time, and in primary alcohol it will not react. Okay, if you further heat this, then it can react. Okay, so basically it proceeds through SN1 mechanism. Okay, as a result of this, 3 degree carbocation generates quickly and you will get product quickly. Okay, so let's go ahead. Okay, so these reactions are very important. Just have a look on this. If you are having chromic oxide, then basically this is chromic oxide oxidation. Okay, so CH2OH can be converted to aldehyde. If you are giving 2 degree alcohol, you can get ketone. Always remember, 1 degree alcohol aldehyde, 2 degree alcohol ketone. Okay, now pyridinium chlorochromate. Okay, PCC, pyridinium chlorochromate. Okay, that will give you aldehyde. Okay, this is very important, copper at 573 Kelvin. Okay, so if you are having 1 degree alcohol, in presence of copper you will get aldehyde. 2 degree alcohol will give you ketone. Here comes a fun about 3 degree alcohol. 3 degree alcohol will give you alkene. Okay, and from here they ask the question. Okay, so from 3 degree alcohol you will end up with alkene. I guess this is clear to you. Let's go ahead. Okay, see, this is a question. What happens when vapors of 1 degree, 2 degree and 3 degree alcohol passed over heated copper at 573 Kelvin? Important question for this year. Okay, so you have to just go ahead with this thing. Okay, be careful. 3 degree alcohol in presence of copper will give you alkene. Okay, let's go ahead. What is rectified spirit? What is absolute alcohol? What is denaturation of alcohol? Okay, so this is like a direct question. Rectified spirit means 95.5% ethanol and 4.5% alcohol. Absolute alcohol means 100% pure ethanol. Denaturation of alcohol means commercially alcohol they made it unfit for drinking by mixing copper sulfate and pyridine. Okay, so this is basically the denaturation of alcohol. Important question. Okay, let's go ahead. Describe the manufacture of ethanol from the fermentation of the sugar. Sugar. So basically what we do, sugar in molasses, that or something from the sugar cane. So at first, is it visible properly? I guess yes. Okay, so first we this is converted to glucose and fructose at first. So what enzyme we need for that case? Invertase I need. Okay, so first what you have to take? You have to take molasses or sugarcane. Okay, from there you have to just add invertase. You will end up with glucose and fructose, right? So now whatever you are having, glucose and fructose, you have to ferment that. Okay, in presence of the enzyme zymase. Okay, that zymase you can get it from yeast. So that zymase is mixed in this particular glucose and fructose, and you will end up with the alcohol, ethanol. Okay, I guess this is clear to you. Important question. Okay, let's go ahead. This is the preparation of phenols. Okay, so here you can see from where you can prepare phenol. This is the hydrolysis of the chlorobenzene. So NaOH you can make at first, ONA plus, then HCl, you will end up with alcohol. From the amine, right, aniline, diazotization you do, then give water, you will end up with phenol. This is a very important path. This path is very important. That is cumene to phenol synthesis. Cumene to phenol synthesis. So whenever you are doing cumene to phenol synthesis, phenol plus acetone also you will get. Okay, phenol plus acetone. Okay, remember this particular mechanism is very important. So another one, what is the IUPAC name of cumene? Cumene is isopropyl benzene. In presence of oxygen, you will end up with cumene hydroperoxide. Cumene hydroperoxide, on being hydrolyzed, you will end up with phenol plus acetone. Okay, next here you can see you can proceed with the sulfonation as well. Benzene, treat it with oleum, means do the sulfonation, then NaOH in presence of H plus can give you the phenol. So these mechanisms, these reactions are enough, okay, for the preparation of phenols. Next, these are the questions from the phenol. How would you prepare phenol from benzene via sulfonation? I discussed. From benzene, do the sulfonation, treating it with oleum, then treat it with NaOH. Okay, next, how would you prepare phenol from the diazonium salt? Very important question for this year. Okay, that also I told in the last slide. From aniline, you just go ahead with the diazotization, treat it with water, you will end up with phenol. Next question, how would you prepare phenol from cumene? It's a super important question. Okay, cumene to phenol synthesis, that also I discussed. Okay, who is saying Sandmeyer's reaction? It's Pradyun. Pradyun, Sandmeyer's reaction basically we do in presence of cupric halide. Okay, sorry, not cupric, cuprous halide. Okay, so from Sandmeyer's reaction you can't prepare phenol. Okay, Sandmeyer's reaction you can prepare aryl halides, not phenol. Okay, I guess this is clear to you. The reagent you remember, Cu2Cl2 HCl. Okay, not water, right? Let's go ahead. Okay, so these are the reaction I already told you though. So these are the whole reaction you can see. This is the cumene to phenol synthesis. Okay, phenol plus acetone. This byproduct is very important. So from here the question comes. We did it in the MCQ session. Go ahead. Okay. Alcohols are less acidic than phenols. Okay, what is the reason? Alcohols are less acidic than phenols. What is the reason? First of all, whenever you will see the phenol, in alcohols, normal alcohols, alkoxide ions you will get, but in phenol, phenoxide ion you will get, right? Now this phenoxide ion is resonance stabilized, right? So the conjugate base that you are getting after releasing of H plus for phenol, the phenoxide ion, that is resonance stabilized. Hence phenol is better acid than that of the alcohol. Next, give a chemical reaction to show phenols are more acidic than that of the water. You can go ahead with the NaOH reaction. Okay, water will not react, but this thing, phenol will react with NaOH to give you sodium phenoxide, ONA. Okay, okay, very good, Pradyun. Let's go ahead. Okay, This question again important one, you have to tell me the answer. What is the effect of the following groups on acidity of phenol? First one is CH3, next one is NO2. This is basically electron donating group and this is electron withdrawing group. So in presence of electron donating group, acidity decreases. In presence of electron withdrawing group, acidity increases. I guess this is clear to you. Let's go ahead. Among orthonitrophenol and phenol, which is having higher pKa value? So orthonitrophenol, I guess you know, it is having an electron, orthonitrophenol, it is having an electron withdrawing group. Just now I told you electron withdrawing group means acidity is more, pKa is less, right? Hence phenol is having higher pKa, right? I guess it is clear. Okay, very good. Amaya, very good. Okay, let's go ahead. This is the reaction of cleavage of OH bond. I already told, I guess. Yeah, let's go ahead with the questions. How do you prepare aspirin from salicylic acid? I don't have to tell you how much important this question is, and give the IUPAC name of the aspirin. Okay, so yeah, this is the reaction. Where is the reaction? This is the reaction. So basically salicylic acid, if you treat this, if you have to do reflux, basically in presence of acetic anhydride, you will end with like aspirin. Okay, so what is the name, IUPAC name of aspirin? That is basically 2-acetoxy-benzic acid. 2-acetoxy-benzoic acid. Let's go ahead. Okay, these are the reactions of phenol. All sets of reactions are here. Okay, so let me tell you first this reaction. Tell me the name of this reaction where I am getting salicylic acid. First one, this is the bromination in phenol. Okay, this is the bromination in presence of CS2 and this is Br2 in presence of water. Okay, and this is Br2 in presence of CS2, carbon disulfide. So if bromination in presence of water, bromine water, you will get both ortho-para substitution, but bromine in presence of carbon disulfide, either ortho and para mixture you will get. Concentrated HNO3 will give you all ortho-para substitution. Diluted HNO3 will give you ortho plus para. And this is the reaction with NaOH and Na. Okay, very good, Amaya. It's a Coles reaction, right? One more reaction is there. Okay, that is Riemann-Tiemann. That also we will come. Okay, electrophilic substitution of phenol occurs at the ortho and para position. Give reason, because you can see while resonating, it increases the electron density in the ortho and the para position only. Ortho and in the para position, you can see the negative sign is coming, right? So if any electrophile wants to enter, then definitely it will choose the maximum electron dense system. So ortho-para directing. I guess it's clear. Let's go ahead. Among ortho and para-nitrophenol, which has higher boiling point, higher vapor pressure. Ortho and para-nitrophenol, if you see, para-nitrophenol will be having the higher boiling point. Why? Because they can form intermolecular hydrogen bonding. What is the reason? Intermolecular hydrogen bonding. Okay, to break them you need more energy. Next, higher vapor pressure. Higher vapor pressure you will get orthonitrophenol because they form intramolecular hydrogen bonding. Okay, they are steam volatile, right? Yes, if you draw the resonating structure, then if you show them that yes, in this position, in the ortho and para, the electron density increases, then it will be better actually. Okay, it's a better approach. Okay, let's go. Next, orthonitrophenol is steam volatile but not para-nitrophenol. I guess you know this question is very important. Okay, explain why. Because orthonitrophenol, just now I discussed, it forms intramolecular hydrogen bonding, but para-nitrophenol, they form intermolecular hydrogen bonding. To separate them, we use the steam distillation method, right? Let's go ahead. Name the products formed when phenol treated with first bromine water, then bromine in CS2, CCl4. So bromine water you will get both ortho and para substitution. Sorry. For the bromine water you will get this. This, right? And for this case you will end up with the mixture of ortho and para. I guess this is clear to you. Okay, so this is the Reimer-Tiemann reaction, salicylaldehyde. Okay, very important. Here whatever the reaction, this particular slide is super important. This particular question also comes if phenol is further oxidized in presence of Na2Cr2O7, you will end up with benzoquinone. Okay, this is oxidized phenol. And if you treat this with zinc dust, you will get back your phenol. And this is, I am not explaining further, this is your Reimer-Tiemann reaction, right? Let's go. Explain Cole's reaction, or how do you convert phenol to salicylic acid? I guess this is clear to you, I don't have to tell you further. Okay, so this is ONA, CO2, and this is the salicylic acid you will end up. Okay, any question? Reimer-Tiemann, ortho or para-bromophenol, very good. Supriya is asking, ma'am, Ekta ma'am won't take. Okay, Ekta ma'am, actually Ekta ma'am is for up to 10th grade. I requested her last day to do the video for your 2 and 3 marker because I was little bit occupied. So that's the reason she came. But no, she will not take the live session. But if you want further, then I can request her. Okay, because here itself for the KCET and your level, I am the teacher for the chemistry. Okay, let's go ahead. Okay, so what is Reimer-Tiemann reaction? Just a minute. Okay, what is Reimer-Tiemann reaction? With example, I guess it's clear to you. I don't have to explain this. Let's go. Okay, name the product formed when phenol treated with first CHCl3 in presence of NaOH followed by hydrolysis. I guess you know what reaction, Reimer-Tiemann. Next, CCl4 in presence of NaOH followed by hydrolysis. So this will also give you the salicylic acid. Okay, CCl4 in presence of NaOH followed by hydrolysis will also give you salicylic acid. Okay, let's go ahead. What happens when phenol is treated with zinc dust? It will give you the benzene. Explain the oxidation of phenol. That's what I told you. Phenol in presence of K2Cr2O7 or Na2Cr2O7, it will give you the benzoquinone. Okay, so I guess this is clear. Next, explain Williamson ether synthesis with an example. Very important, huh? So here you can see alkyl halide on heating with alkoxide. So here you can see O minus is there, O minus will react here, Cl will leave. This is an SN2 based mechanism. This is one SN2 based mechanism. This is ROR. Okay, I guess this is clear for you. Let's go ahead. Okay, which of the following is better method for preparation of tertiary butyl ethyl ether? Tertiary butyl ethyl ether. Okay, so tell me either this method or this method. Okay, so basically let me tell you, this will follow Williamson ether synthesis, right? And Williamson ether synthesis is basically an SN2 mechanism. So check for the halide where there are less steric hindrance. Okay, because backside attack I need to do, so look for this case. Okay, so if I am having a bulky nucleophile, that's fine, but check this one, CH3, CH2, Cl. There is no steric hindrance backside. So now see CH3 whole thrice, O minus. This will attack here and chlorine will leave nicely. So backside of the alkyl halide should be opened. Okay, as a result of this, you will end up with the product that is CH3, CH2, here oxygen, here C, CH3, CH3, CH3. Okay, tertiary butyl ethyl ether. Second method, very good. Okay, very good. Let's go ahead. Next, this is a very important question. What happens when diethyl ether is heated with first limited amount of HI and then excess amount of HI? So diethyl ether, CH3, CH2, O, CH2, CH3. Okay, so first I will do limited HI. Limited HI if I give, then I will end up with one alcohol and one iodide. CH3, CH2, OH plus CH3, CH2, I. Now, if I give excess HI, then this alcohol will also get converted to iodide as well. So, CH3, CH2, OH, if I further give HI here, then this OH will be converted to I through SN2 mechanism. CH3, CH2, I. Okay, I guess this is clear. Let's go ahead. Okay, this is a mechanism, a little bit messy it has become. Wait, let me clear this. Okay, now you can go through it. I guess it is clear to you people. Okay. Let's go ahead. Okay, again that type of question you can see. Complete the following and mention whether the reaction is SN1 and SN2. Okay, so for this case, again, which case I will get alcohol and which case I will get iodide, right? So definitely this particular thing I will get the alcohol, right? So you will end up with CH3, C, CH3, CH3. Here you will get what? Tell me. It is SN1, definitely it is going to be SN1. Here you will end up with iodide or OH, that you tell me. Tertiary alcohol, very good. You will end up with tertiary alcohol plus CH3I. I guess this is clear to you people. So this is basically your SN1 mechanism. Let's go ahead. Wait. We did something wrong here. This will proceed through SN2 mechanism basically. Okay, so here is a twist for this question. Okay, just go through the explanation once. The reaction of an ether with HI typically proceeds through SN2 mechanism where the iodide ion attacks less sterically hindered alkyl group. Fine. But in this specific case, the ether has a tertiary alkyl group, right? So the protonation of the oxygen is followed by cleavage. So at first the protonation will take place, means here I will get the OH plus. The protonation will take place at first, right? And it will follow the carbocation formation. So once the protonation will take place, then this thing will leave the system. So this thing will leave the system as a result of this CH3, CH3, here CH3, here you will be having carbocation, right? And here you will be having OCH3 plus. So definitely I minus is there. I minus will attack over here, okay, and H plus, it will take the H plus. So I will end up with tertiary butyl iodide. Okay, I will end up with tertiary butyl iodide along with CH3OH. Now I guess it is clear to you. Yeah, very good, Pradyun. I guess this is clear now. Let's go ahead. So how is HX reacts with alkyl or aryl ether? Explain with an example. So I'm not going for a further thing because it is the same thing. You can see this is your alkyl aryl ether. Okay, so you will end up with the RX and phenol. Okay, this is one example. Anisole, if you are having HI in presence of HI, you will end up with phenol and methyl iodide. Let's go ahead. Okay, anisole undergoes electrophilic substitution at the ortho-para position, again the same reason, because in the ortho and para position you can see the negative sign comes, the negative charge density increases, hence it is ortho-para directing. Go ahead. Explain the nitration of anisole. Explain the bromination. Okay, so this is the nitration reaction. You can see you can get the para-nitro and ortho-nitro as well. Okay, so this is the mechanism. So what basically happens here? So this nitro group, first OCH3 group actually takes part in resonance, and the pi electron cloud attacks on the NO2 plus as an electrophile. Okay, here NO2 plus is your electrophile. So now this NO2 plus, this complex is attached, this nucleophile is, this electrophile is attached over here. Okay, this particular complex is called sigma complex. Now water takes up the hydrogen and you will get back the aromaticity. Okay, this is your para-nitroanisole. So basically for this case, for a little bit advancement for the answer, I just kept the reaction mechanism, but in case you are writing only the para plus ortho product, that will be more than enough for you. Okay, let's go ahead. This is the bromination product. For both ortho and para it is observed. So you can see again pi electron cloud will attack on Br plus. Okay, and the this will form the sigma complex. This hydrogen bond will jump back to give back the aromaticity. Okay, ortho plus para. I guess this is clear. Let's go. Explain Friedel-Crafts alkylation of anisole and acylation. Okay, so this is your alkylation reaction. So like the similar way you can write the nitro and bromo product as well. Okay, without writing the mechanism. If you write, then definitely your examiner will be impressed. Okay, so I guess this is clear for you. Just ortho and para product you can add. Next, this is your acylation product, again ortho and para. I guess it is clear. IUPAC name for it. What is, in which case? For this case, you can see here it is already written 4-methoxytoluene. So this is your methoxy group and toluene. Okay, so like that you can name this. Already it is written. Once you will just download the PDF, you will get it. Okay, let's go ahead. Okay, very important question. 5 marker. Explain the mechanism of dehydration of ethanol to ethene. Dehydration of ethanol to ethene. Okay, so this is the dehydration method. First is protonation. So OH will takes up one hydrogen, it will form protonated alcohol. Then protonated alcohol, OH2 plus being a very good leaving group, it will leave the system generating a carbocation. Now this carbon hydrogen bond will jump back to give you the ethene. Okay, remember, very important, the mechanism you have to go through. Okay, let's go. Next, identify A and B. Fine, B you know already. B you just comment me. By the time, let me just A also you know. A also you tell me. CO2 means you will end up with salicylic acid, right? You will end up with, your A is basically salicylic acid. And this is OH, right? So for this case you will get ethanol plus CH3, here also CH3, and here you will end up with I. Very important problem for this year. I guess this is clear. No, for organic chemistry, you don't need to balance it. It's fine. But for inorganic, whatever the reaction you will write, let's say you are writing the reaction for the KMNO4, K2Cr2O7, you must balance them. And anode cathode reaction, you have to balance. Okay, let's go. Important question. You can see bromine water, right? So you will end up with okay. Now zinc dust, in presence of zinc dust, you will end up with normal phenol. Okay, so this thing you tell me. Who will tell me the question number 3? Someone please tell me the question number 3. What is the answer of question number 3? Anyone? Pradyun? This is basically, Amaya is saying H2O. Okay, very good. This is going to be your H2O, right? I guess this is clear to you. Next, how to prepare phenol from aniline. That also I told you. So basically, aniline, from there diazotize it. This is a very important thing, huh? Very important question. N2 plus Cl minus, from there give water, you will end up with phenol. Okay, I guess this is clear for you. Let's go ahead. Okay, explain the mechanism of dehydration of alcohols into ether. So this is the mechanism. So be careful. Here the second step a little bit different. First step is definitely protonation of alcohol. Second step is basically this lone pair will attack. It will do SN2 attack, and then this OH2 plus will leave. Okay, and you will end up with the protonated version like that. Then this proton will jump. I mean the oxygen hydrogen bond will jump here and hydrogen will leave the system. This is your ether. Very important. Okay, very important question. How anisole react with acetyl chloride? How anisole react with acetyl chloride? So basically, if you are having anisole OCH3, acetyl chloride means CH3 COCl. In presence of aluminium chloride, they will react Friedel-Crafts acylation. So here OCH3 you will get, in the ortho you will get COCH3, and in the para also you will get COCH3. Here OCH3 I am having, in the para also I will get COCH3. I guess it is clear. 37A. 37A you did not understand? Okay, let me just explain you. Let's say I am having this alcohol CH3 CH2 OH. Okay, so what you have to do first, you have to protonate this, means you have to treat this with a H plus, right? Then you will end up with CH3 CH2 O, here one hydrogen plus, right? Now I have more ethanol in my medium as well, na? Definitely I am not having only one ethanol. So many ethanols are there. So one more ethanol you take, CH3 CH2 OH. This OH has lone pair, right? And I am having this species in my media as well. So CH3 CH2 OH plus. So now this oxygen, this is basically SN2 attack here. This oxygen acts as a nucleophile and it will attack over here, and this will leave the system. Okay, now after attacking, what will be the product? Right from here, CH3 CH2 CH2, right? Now with this carbon, the oxygen will be attached, OH group. So OH, let's attach here CH2, then CH3. Like that you write. Okay. Now this oxygen is having 3 hand, so definitely it's gonna be plus. Okay. Now next step is removal of one hydrogen. So this, because oxygen cannot stay in the plus state, right? As a result of this, this oxygen hydrogen bond jumps back and hydrogen leaves the system, and you will get back your ether, diethyl ether. CH2O, CH2, CH3. Okay, I guess it is clear to you, Pradyun. Just let me know if you understood this or not. Okay, let's go. Okay, for this reaction, explain the mechanism of hydration of alkenes to alcohol. Again, I am not discussing that. Okay, so for this case, here what you will get, I told you this is a Markovnikov mechanism. So A is going to be CH3, C, here OH, here CH, CH3. Markovnikov mechanism. Further, just now I told you chromic oxide oxidation. What you will get? 2-degree alcohol, right? It is a 2-degree alcohol. You will end up with ketone, right? You will end up with ketone. No, it's not aldehyde basically. It's going to be ketone. Carbonyl you will end up because you are starting with a 2-degree alcohol. Okay, Amaya? Is it clear? This is your ethene alkene to alcohol. Look at the mechanism. Okay, this is the very common mechanism, important as well. So first what you have to do, first protonated water, H3O plus you are having, right? So this alkene double bond will attack on the hydrogen and this OH2 plus will leave the system in the form of H2O. So you will end up with a carbocation generation. Now on this carbocation, water will attack as a nucleophile, right? So again here you will end up with a OH2 plus. Now what will happen? Water will takes up the hydrogen and the oxygen hydrogen electron will jump back to give you the alcohol. Okay, I guess this is clear to you. Yes, let's go ahead. Just let me know if it is clear. Okay, so here comes your favorite type. An alkene C3H6 reacts with, just a minute, give me a minute. Okay. Okay, so let's go ahead with this problem. An alkene X, that is C3H6. C3H6 means alkene, propene. That's it. So let's go ahead with X. So X must be this CH3. What is the formula of propene? Why I am thinking so much? CH double bond CH2. That's it. This is your X. Reacts with H2 in presence of H plus. Just now we did H plus in presence of H2. What I will get? I will get alcohol. Here one OH. Okay, here H. This is CH3. Fine. This is your Y. Okay. Now further reaction with CrO3. Oh, just now we did CrO3 in presence of H plus to produce compound Z. So what it will produce? It will produce ketone, right? CH3, C double bond O, CH3. This is your Z. Write the IUPAC name of XYZ. X is basically propene, right? What is X? X is propene. Okay, for this case 1, 2, 3, 2 propanol. Okay, for this case this is your acetone. What is the name of Z? What is the name of Z? Who can tell me what is IUPAC name of Z? This is also propanone, you can write. Okay, very good, very good. This is basically propanone. Fine. Now, which among the following compounds have lowest and highest pK value? Okay, para-nitrophenol. This is your para-nitrophenol. Para-nitrophenol. Okay, next phenol. Okay, next ethanol. CH3, CH2, OH and orthocresol. Okay, now tell me which one will be having the highest and lowest. So definitely lowest pK is going to be for this because electron withdrawing group is there. So this is for the lowest pK. Lowest pK. Now highest pK for what? Highest pK either for the ethanol or for the cresol, that you tell me. Fast. Highest for the toluene. Where toluene? Okay, highest for the cresol. Very good. Here I am having an electron donating group, right? So this is the highest one. Acidity less. I guess this is clear for you. Okay, let's go ahead. Okay, how is phenol prepared from benzene sulfonic acid? I already discussed this thing. Okay, this reaction, how anisole reacts with methyl chloride. So wait, how anisole reacts with methyl chloride and what is the effect of electron donating group? Okay, methyl chloride. Anisole react with methyl chloride, that is basically Friedel-Crafts alkylation. If you are having OCH3 plus CH3Cl in presence of aluminium chloride, I will end up with ortho and para substitution OCH3. Here I will get CH3 and one more thing OCH3. Here you will get CH3. That's it. Okay, what is the effect of electron donating group? You know electron donating group, what it does? It reduces the acidity. Right? I guess this is clear for you. Let's go. So these are the important thing. I guess you people can't see this screen properly. Anyway, whenever you will get it, then definitely you can see that. So what are the important zone out of it? Williamson ether synthesis, Coles electrolysis, Raymer-Tiemann, Friedel-Crafts and esterification. For the mechanism, must do mechanisms are dehydration of alcohol to ether, and hydrogenation of alkenes to alcohol. Okay, so these are the important reactions and the mechanism that you have to go through. Further we will go ahead with the aldehydes, ketones and carboxylic acid. Okay, I will give you 5 to 6 minutes, 5 to 8 minutes, not more, 5 to 8 minutes break, because we have to do full revision as well. Okay, we have to finish it earlier. I will go ahead with the 5 to 8 minutes break. By that time, come up with your lunch, what it calls, lunch plate, and have your lunch and do the session. That's it. please come back. We can start now. Come back, all of you, please come back. We can start now. We have to finish the aldehyde, ketones, amines and biomolecules. Small chapters, but it's okay. Okay, let's go ahead. Okay, so you can see it's a very heavy weighted chapter. 12 mark is going to come from here. Okay, so let's go ahead with this. So here you can see first question, how would you, I will go a little faster, okay. So because in the evening again I am telling you that one session is there for the complete revision, 1 ghante or 1.5 ghante hardly, okay. But here this chapter is quite easier. Some name reactions are very important. So for those cases we will focus whatever the mechanism and all that we already finished. Okay. Now you can see how would you prepare the aldehydes from acetyl chloride or benzoyl chloride. Important question. Okay. So acetyl chloride on reduction with H2 in presence of PD catalyst. That is Rosenmund reaction, right? Rosenmund reaction, name reaction, right? Important question. Okay. Next, how would you prepare aldehydes from nitriles? So that is basically your Stephens reaction. So that is basically your Stephens reaction. You can see RCN in presence of SnCl2 and HCl can give you RCHO, right? Next question. Name the reagent or oxidizing agent used in Etard's reaction. Very important. That's going to be chromyl chloride. Okay. If you are having toluene, you can end up with aldehyde, benzaldehyde. Next, you can see what is Etard's reaction. Explain. So important. Again, this is the Etard reaction. You can see in presence of CrO2Cl2 and carbon disulfide. First, it forms a chromium complex and it ends up with benzaldehyde. Very important question. How would you convert toluene into benzaldehyde? By using chromic oxide. So here you can see toluene, it reacts with CrO3 as well in presence of acetic anhydride to give you the benzaldehyde. Okay. Next, carbonyl group is more susceptible to the attack of nucleophile. Why? Because as you can see here, I have drawn a small diagram. Here carbon, you can see because of the presence of oxygen, oxygen pulls the electron cloud density towards itself, making the carbon electronically poor. Right? As a result of this, any nucleophile, when it wants to come, it can come either from top or from bottom. Okay, so it can react. It makes the carbon susceptible for the nucleophilic attack. Let's go ahead. Okay. Next, explain the commercial method of manufacturing of benzaldehyde by side chain chlorination. Very important, my dear, this question. Hey, Mr. Lucky, whose request you want here? If you don't feel like you should study, don't just waste time here. Okay, so you can go to some other live session and you can do the mess over there, not here. Here people are really studying, they're learning. Okay, if you want to learn, be here, otherwise don't message and don't create mess here. Okay. So let's go ahead. Explain the commercial method of manufacturing benzaldehyde by the side chain chlorination. So here you can see the mechanism is very important. In toluene, basically if you do the side chain chlorination first, then in presence of chlorine and H nu, it will form benzyl chloride, CHCl2, benzene with CHCl2. Now in presence of water, it will form the benzaldehyde. Very important reaction. Next, explain Gattermann-Koch. I guess you know this Gattermann-Koch reaction. In benzene in presence of CO, HCl and anhydride AlCl3, it will form the benzaldehyde. Next, how would you prepare aldehydes from ester? So basically you can use dibutyl H. So dibutyl H means diisobutyl aluminium hydride. Okay, so you can see this is the ester. You can use the dibutyl H out of it and you can end up with the aldehyde. Okay, I guess this is clear. Let's go ahead. Aldehydes are more reactive than that of the ketone for nucleophilic addition. Why? Because of the steric hindrance. You can see steric effect and electronic effect. Okay, so electron donating groups are there in ketone, right? 2 R groups are there, so 2 R groups make the carbon negative, right, for ketone. So that's better in case of aldehyde, right? So aldehyde is more reactive. Next, benzaldehyde is less reactive towards nucleophilic addition reaction. Why? Because of the resonance through benzene. Okay, so resonance, due to the resonance, the polarity of carbon in CO that reduces, carbon becomes negative. Okay, next, higher ketones like acetophenone do not react with NaHSO3. Why? Because of the steric hindrance. Okay, big ketone, if you are having the bigger ketone like too bulky group, then HSO3 minus, this entire big nucleophile, how it will react, where it will get space. So yeah, let's go ahead. What is a Clemmensen reduction? Give example. Next, what is Wolff-Kishner reduction? These are the name reaction. You can see first one is the Clemmensen. Okay, so first one is, you can see, if you are having zinc amalgam HCl, so basically you have to start with the carbonyl in presence of zinc amalgam and HCl. You will end up with CH2. Okay, next, B, what is Wolff-Kishner reduction? Give an example. Wolff-Kishner reduction is basically hydrazine in presence of ethylene glycol, the same thing. So again, carbonyl compound you are having hydrazine, if you take NH2 in presence of ethylene glycol, so you will end up with CH2. Okay, next, name the reagent that is used for characterization of aldehyde and ketone, that you can use as 2,4-DNP. Okay, I guess this is clear. Let's go ahead. Explain the tests to distinguish between aldehyde and ketone. Very important. Okay, so what we can do the tolerance test. Okay, aldehyde on treating with the tolerance reagent gives silver mirror precipitation, but ketone will not react here. Next, aromatic aldehydes do not answer in Felling's test. Why? Because it will undergo Cannizzaro reaction. Okay, instead of proceeding for the carboxylate formation and Cu2O precipitation for the Felling's test, okay, it will undergo Cannizzaro reaction because it has alpha hydrogen. Okay, so I guess it is clear for you. You understood this. Any doubt, please let me know. What's going on here? Okay, fine. What the hell you people are doing here? My goodness. Okay, let's go ahead anyway. So what is haloform reaction? Give an example. Next, why is isopropyl alcohol undergo haloform reaction? Very important question is this. Okay, so if you are having methyl ketone unit, see here you can see one COCH3, this is basically one methyl keto unit. So in presence of methyl keto unit, one NaOH and I2, okay, or any X, any halogen, okay, they will form the haloform. Okay, so haloform, in case you are using I, okay, it will form CHI3. It means it will give you a yellow colored precipitation. Okay, so once you are just doing the reaction in like I2 in presence of NaOH, you will end up with iodoform. Iodoform will give you some yellow coloration. So it means that your compound is containing methyl ketone unit. Okay, let's go. So here you can see, is isopropyl alcohol undergo haloform reaction? The reason is yes, It is an alcohol, but still it undergoes the reaction, because in presence of I2 and NaOH, first it will form the ketone. Okay, so under this reaction condition, first it will form the ketone, and then you are getting one methyl keto unit. You can see you are getting one methyl keto unit, and that methyl keto unit further will give you the haloform, iodoform test positive. Okay, I guess it is clear to you. Let's go ahead. Okay, so what is aldol condensation reaction? Give example. So aldol condensation reaction, you basically need one alpha hydrogen. Okay, so just let me know if you know how to write the aldol condensation product, or I should show it once. Just let me know if you want me to show the, okay, just let me know if you want me to show the aldol product or not. Okay, show. Fine. So here, let's say how you should write, I am showing you the technique. Okay, let's say I am having aldehyde, CH3 COH. Okay, first I will show you the normal aldol, then cross aldol. Okay, so this is the self aldol. Okay, so another unit of same molecule you take. How you should write that? See, so the methyl group I will write like this: hydrogen, hydrogen, hydrogen. Here I will write COH. Fine. So now this particular oxygen, let's take, it will take this hydrogen. Okay, so now if it takes this hydrogen, how it will look like? So what is the method? Takes up this hydrogen and make a bond between this carbon and this carbon. Okay, what I said, this oxygen and this hydrogen join them, and this carbon and this carbon make the bond. So see, here you will write O, here one hydrogen, and this carbon you join. So here by default one hydrogen was there. See, here two hydrogen I had, CH2, C double bond O, H. Okay, this is, you can see, this is your alpha, this is your beta. So this is beta hydroxyaldehyde, beta hydroxyaldehyde. Okay, further if you heat the system, what happens, you know? Let me just break it down a little bit. This particular carbon, it has one hydrogen. Okay, they undergoes dehydration. So these particular oxygen, hydrogen and these hydrogen, they forms water, and this bond jumps over here. Okay, so removal of one unit of water. So removal of water, as a result of this you will get an alkene unit here. So CH3 C double bond CH, C double bond O, H. Okay, this is where you will end up. Okay, so here you can see this is your alpha beta. Okay, so the product is alpha beta unsaturated aldehyde. Just let me know if you understood this or not. Just let me know if you understood how to write the aldehyde product or not. Okay, fine. So now we will go with the cross aldol. Okay, so let me just this is one aldehyde. Okay, I will take another aldehyde. Let's say CH3CHO. same way you have to go ahead. Okay, so I need alpha hydrogen, that's why I kept it as benzyl aldehyde, like that. Okay, so this oxygen will takes up this hydrogen, and this carbon you make the bond. So if I go ahead, dilute NaOH is the reagent. Okay, dilute NaOH. So what you have to do here, you will be having CH2 as it is, everything you write. See, with this oxygen you attach one hydrogen, this carbon already had one hydrogen, this carbon and this carbon you attach. Okay, along with that two more hydrogen, then CHO. Okay, this is your crossed aldol product. Okay, this is your crossed aldol. I guess it is clear. So now again, if you heat this from here OH and from here hydrogen, one hydrogen will be removed to give you one double bond, dehydration. Okay, so if you further heat this, you will end up with alpha beta unsaturated aldehyde. Okay, alpha beta unsaturated aldehyde. Just let me know if you understood or not. The crossed aldol, if you understood or not, just let me know. Okay, fine. So let's go ahead. I guess this is clear. This is how you should write the product, okay, for the alcohol, sorry, for aldol. What is Cannizzaro reaction? Give an example. So Cannizzaro reaction is what? Whenever you are having one aldehyde which is not having any alpha hydrogen, aldehyde without any alpha hydrogen, it will undergo disproportionation reaction. Here I gave one example. You can see benzaldehyde in presence of concentrated NaOH you need here. Okay, it will form the benzoate anion and the alcohol. Okay, that's it. Next, which type of aldehyde will undergo Cannizzaro? I don't think that I have to tell this. Sorry. So the aldehyde which is having no alpha hydrogen, right? Next, why acetaldehyde does not undergo Cannizzaro? So acetaldehyde, if you draw, acetaldehyde is having 3 alpha hydrogen. Why it will undergo Cannizzaro? It is having 3 alpha hydrogen, right? So it should not undergo Cannizzaro, right? I guess it is clear. Let's go ahead. How would you prepare carboxylic acid from 1 degree alcohol? So 1 degree alcohol in presence of dry what it calls dry ice can give you carboxylic acid. Okay, let's explain with an example. Okay, sorry. 1 degree alcohol, you can directly treat this with KMnO4 or K2Cr2O7. Do not need to go for the, Grignard reagent. Grignard reagent also can help you. Okay. Anyway, carboxylic acid can be prepared from 1 degree alcohol by using a strong oxidizing agent like K2Cr2O7 or KMnO4. Okay, carboxylic acid from the nitriles. Okay, so nitriles, let me show you. If you are having CH3CN, now it can be hydrolyzed to amide. Let's say hydrolysis, right? So H plus in presence of H2O if I do, then it can form CH3, sorry, CO NH2. Okay, so further if you treat this with H plus or OH minus, okay, it can give you the carboxylic acid CH3COOH. Okay, next, how do you prepare carboxylic acid from the Grignard reagent? Okay, that's what I was telling actually. So Grignard reagent, you have to go ahead with the dry ice. Okay, so let me show you the reaction. Dry ice to give you the carboxylic acid. Anyway, let's say I am having CH3 Mg beer, right? CH3 Mg beer. Dry ice means carbon dioxide. So this is my carbon dioxide. Okay, this CH3 will attack here, this will open up. As a result of this, I will end up with something like this. See here CH3, here I will be having OMgBr, here as it is double bond O. Further, if I do the hydrolysis, means H3O plus, if I give, then see, I will end up with a carboxylic acid. C double bond O, here I am having OH and here I am having CH3 group. Okay, I guess this is clear. This is the reaction. Okay, let's go ahead. How do you convert acetic acid to acetamide? Okay, so basically, wait, sorry. Acetic acid to acetamide, fine. So if I am having acetic acid, CH3, C double bond OH, I have to treat this with NH3, means ammonia. That will give you CH3, C double bond O minus NH4 plus. Heat the system, that will give you acetamide, CH3, C double bond O, NH2. Okay, I guess this is clear. How do you convert phthalic acid into phthalimide? Very important question. Okay, so phthalic acid in the same way, you can see if you react with NH3, it will form this thing, CO minus NH4 plus, both the cases. Further, if you heat, this is phthalimide, right? Strong heating, from these two, one ammonia will be released and you will end up with phthalimide. Okay, so let's go. I guess it is clear. Let's go ahead. What is decarboxylation reaction? Give an example. So decarboxylation is basically the process of removing CO2 from its sodium salt of carboxylic acid. What we will use? We will use decarboxylating reagent, that is soda lime. Okay, so this is a reaction, you can see RCONA it was. So it is a basically step down process because removal of one carbon takes place. Next, name the product formed when the sodium acetate is heated with soda lime. Again the same thing you can see. So sodium acetate, if I just go ahead, CH3 COONA. Okay, if I heat this with soda lime means NaOH plus CaO. NaOH plus CaO, if I heat this thing, then I will end up with CH4. Okay, I will end up with CH4. Give one name of the decarboxylating reagent, that is soda lime, you can take. I guess it is clear to you. Let's go ahead. What is HBZ reaction? Nitration of benzoic acid and bromination of benzoic acid. Okay, first let's discuss about the HBZ reaction. Here you can see alpha halocarboxylic acid, you will end up Haloarene. So basically this is my alpha carbon, right? So in the alpha carbon the halogen will be added. Okay, next explain the nitration. So nitration, always remember, COOH is basically a meta-directing group. Okay, it's a meta-directing group. So this, if you treat this with HNO3 or strong concentrated HNO3 plus H2SO4, then you will end up with meta-nitrobenzoic acid. Okay, for the bromination also it is the same thing. Okay, let's go ahead. Okay, so we are done with the aldehyde ketone. So basically this is a very small chapter, very precise amount of question we did, and you will get common out of it, don't worry. Okay, so Rosenman, Stephen, Ettard, Clemenson and Wolff-Kishner, important reaction, aldol, Carnigero, HBZ, decarboxylation, tollens and Fellings, important. Okay, and mechanism, this is one important thing, that mechanism of nucleophilic addition. Okay, so let me just show it to you a little bit. Let's say I am having this type of thing. Now they will ask you if you add this with HCN. Okay, so CN minus will act as a nucleophile, so CN minus will act here and you will end up with something like this. So with CN and here with O minus. Further, on being protonated, it can give you cyanohydrine. It can give you CN, it can give you the cyanohydrine. Very important, okay? Very important thing, that's why I felt I should tell. Okay, this thing you don't have to see, don't worry. Okay, these are the names. Okay, just look at what I'm doing here. This is basically the nucleophilic reaction. Okay, so I guess it is clear. Let's go ahead. Okay, amines, very fixed reaction we will do. Small chapter but very precise thing we can get out of it. No 5-minute break. Just now we ended up with a 10 minutes break. After that, after amines we will give 5 minutes break. Amines will be finished fast. Okay, see which type of amines answer carbylamine reaction? That is primary amine, right? Primary amine will give you the carbylamine test. Next, explain the reaction. So this is the entire reaction. Here you can see RNH2 in presence of chloroform and KOH, it will give you a foul smell compound, that is isocyanide, plus KCl plus H2O. Okay, next identify the compound X. You can see this is aniline. Aniline in presence of diazotizing reagent. X is basically benzene with diazonium chloride, benzene with N2 plus Cl minus. Okay, now in presence of what, you will end up with benzene with I, right? Here you have to give simple Ki, that's it. Sandmeyer, not Sandmeyer, in presence of Ki you will end up with iodobenzene. I guess this is clear. Let's go ahead. Okay, again you can see HbF4 you have to give. So for that case, definitely you will end up with a benzene with fluorine, right? And then NaNO2 and Cu, it will give you the fluorine, right? And then here you will end up with BF3. Okay, I guess this is clear for you. Sorry. Okay, let's go ahead. IUPAC name of this particular compound. So here you can see this is propanamine. Carbylamine reaction we already discussed. This particular thing, how many carbon? 1, 2, 3. Propanamine. Next, let's go ahead. Explain Hoffman bromamide degradation. Already we did. Those question only repeatedly comes. Okay. Next, discuss the coupling reaction of benzene diazonium chloride with aniline. Okay, let's do that. So, okay, IUPAC nomenclature, here you can see NN, here you can see diethyl pentan 2 amine. So, diethyl, 2 ethyl groups are there. Okay, pent means how many carbon you can see? Total 5 carbon I am having. Pentan in the 2 position I am having amine. Okay, let's go ahead. Okay, this reaction, right? Let me show it here. So I am having benzene diazonium chloride. Benzene this is how you should go ahead with the coupling reaction. Okay, diazonium chloride with aniline. Okay, now you can see Cl minus and H, they will be removed from this thing. Okay, as a result of this, it requires acidic media, remember that, huh? And here you will end up with the coupled product. This one, this is yellow in color. Okay, this is yellow in color. This is called para amino azobenzene. Okay, I guess this is clear. I guess this is clear. Let's go ahead. Okay, so this is the coupling reaction. Okay, let's go ahead. Okay, how do you distinguish between primary, secondary and tertiary amine by using Hindenburg reagent? Very, very important, super important question. Okay, so basically if you are having Hindenburg reagent, let me show you at first. Okay, if you are having Hindenburg reagent, that is benzene sulfonyl chloride, benzene S double bond O, S double bond O, here you are having Cl. Okay, now if I am having, let's say, primary amine, okay, N hydrogen, R hydrogen, like that. Okay, this H and this Cl, they will basically react to give you this thing, benzene S double bond O, here you will be having bonded with nitrogen, here R, here hydrogen. See, I am having one more acidic hydrogen, right? This is acidic hydrogen. I am having one more hydrogen. Okay, as a result of this, it gets dissolved in alkali. It gets dissolved in alkali. So definitely if I am having acidic hydrogen, it will react with alkali, right? Now this is your 1 degree amine, right? Now for the 2 degree amine, I am having only one hydrogen, right? This will react with the sulfonyl chloride and will give you something like this. Now you see, here I am having no hydrogen, no acidic hydrogen. Will it get dissolved in alkali? No. So do not dissolved, do not get dissolved in alkali. Okay, next, if I go ahead with the tertiary one, okay, there is no reaction because here itself no hydrogen, right? So no reaction. Okay, I guess it is clear for you people. I guess it is clear for you people. So let's go ahead, give the preparation of para-hydroxy azobenzene the same way you did it for the last case. Okay, let me just show it here. So let's say I am having benzene diazonium chloride, benzene N double bond, N triple bond plus Cl minus, right? Along with that hydrogen, then benzene ring, here I am having OH. So Cl minus and OH minus, they will go and we will do the coupling now. So this N double bond N, then this. Okay, this is para-hydroxy azobenzene, this is orange in color. Okay, I guess this is clear. Let's go ahead. This is the reaction, you can see. Okay, just let me know if you are having any doubt. If you are having any doubt, just let me know here. Okay, next reaction, Hofmann bromamide. You can see this is your Hofmann bromamide reaction, 1 carbon less system. pKb of aniline is more than that of the methanamine. The reason is methanamine is a better base because aniline lone pair takes part in the resonance, but methanamine you are having one electron donating group, methyl group, right? So that will help the nitrogen to donate the lone pair nicely. Okay, as a result of this, basicity increases, hence pKb less. Okay, so I guess it is clear. Let's go ahead. Okay, this is also written here below, you can check. Go ahead. How would you prepare primary amine by Gabriel thalamide synthesis? Give equation. What are the advantages of this reaction? Give reason. Aromatic amines cannot be prepared from Gabriel thalamide. Very important question, okay? So here you can see B and C. At first you can see 2 degree and 3 degree amine cannot be formed. Only pure primary amine you will get out of this thing. Next reason, because aryl halide, let me just show the reaction, then only you will understand. Because aryl halide, they do not undergo nucleophilic substitution with the anions of thalamide. This is the reaction. Okay, this is the Gabriel thalamide reaction. So this is the anion, N minus. Okay, so now if you are having 2 degree or 3 degree or aryl halide, let's say benzyl, chlorobenzene you are having, it will not react with this anion. Okay, so this is basically what is happening here. SN2 reaction takes place. See, like that, right? So if you are having one benzene ring, so it will not react with that, na? That's the reason it will not react with aryl halide to give you the primary amine. I guess it is clear. Hey, what the hell you are going? Stop spamming, yeah. Anyway, I guess it is clear to you people. Let's go ahead. Fourth point, in the sense I did not get you. Which case you are asking? Fourth point at the end. This one. Which one you are asking? I didn't get you. Can you please tell me? Okay, clear. Fine. Let's go. Okay, so here you can see amines acts as nucleophile, or amines behaves as Lewis base. What is the reason? Because it is having lone pair. Next, aliphatic amines are stronger base than that of the ammonia. Why? Because it is having an electron donating group. Electron donating group increases basicity, right? Here are the reason you can see. Okay, plus I effect means electron donating, right? Next, aromatic amines are weaker base than that of the ammonia. Why? Because the lone pair are involved in the resonance, right? Not ready for the donation. Arrange 1 degree, 2 degree and 3 degree amines in the increasing order of the basicity in aqueous and gaseous. Both of them are very important. These two questions are super important. In gaseous and in aqueous, the trends are different. Gaseous, it's a normal trend, 3 degree, 2 degree, 1 degree. But in aqueous, always remember 2 will come first, then 1, then 3, then normal ammonia. I guess it's clear. Let's go ahead. What is carbylamine reaction? I already told you, not repeating again. How does aliphatic primary amine react with nitrous acid? So basically, aliphatic primary amine, let me show you. CH3, CH2, NH2. Let's say I am having this. Okay, and here I am giving that a diazotizing reagent. What is the reagent? Nitrous acid. From where it will be formed? NaNO2 plus HCl. Okay, 0 to 5 degrees Celsius. You will end up with alcohol, CH3, CH2, OH. Okay, so this same thing I guess I discussed during the MCQ session as well, that benzyl amine, if you are having benzyl means benzene after one CH2 then NH2, then they give the reagent NaNO2 plus HCl, it will form alcohol. It will not form diazotization. Okay, benzene diazonium chloride. I guess it's clear. Let's go ahead. Okay, see, name the product formed when the methylamine reacts with nitrous acid. Okay, so methylamine, okay, the same thing. Here ethylamine I did, you can start with the methylamine. Okay, if it reacts with nitrous acid, you will get CH3OH. Okay, I guess this is clear to you. Methanol, I did it with ethylamine. Okay, what is diazotization? How does aromatic primary amines reacts with nitrous acid? Again the same question. Next, what temperature should be maintained for the diazotization? That is basically 0 to 5 degrees Celsius, or you can say 273 to 278 Kelvin. Any doubt, any doubt, any doubt? Okay. These are the coupling reaction, already I explained. This is just remember the media, it's very important. Sometimes they can ask it in the MCQ. We did it in the MCQ session. Okay, this requires OH minus whenever it is reacting with phenol. In the aniline it requires acidic media, remember that. Next, let's go ahead. Okay, oh my god, I forgot to change the background. I am so sorry. These are some miscellaneous problems will come now, okay, related to all the chapters: haloalkane, haloarenes, alcohols, aldehydes, and this amine. Some miscellaneous problem. Okay, just I'm so sorry for the background. Just tolerate for few minutes. Okay, so then we will go ahead with the biomolecules and then we will finish it up. Okay, so expected by 3:30 we can do it. Okay, so yeah, let's go ahead with the first one. Okay, someone is asking something. Reaction with cadmium chloride and RMGX. Okay, I missed it. Code-house synthesis, right? Okay, don't worry. In the evening session, I will tell you. I will remember this. I will tell you in the evening session. Don't worry. A quick recap we will go. That's not that much important. But yeah, model paper question was there. I forgot that. Okay. I will keep it. Don't worry. So, NaNO2 plus HCl. So, X is basically diazotization, right? N2 plus Cl minus. Further, X on being treated with Ki, it can give you this. So, Y is Ki. I guess there is no doubt. Let's go ahead. This. What is the name of the following reaction? First one is Rosenmund, right? First one is Rosenmund. I'm not good with the spelling, okay? Please, if it is wrong, then please don't comment here. Don't comment here that, ma'am, you are writing wrong spelling. Okay, next here you can see this is Friedel-Crafts acylation. I will not take risk. Friedel-Crafts acylation. Okay, next here you can see this is carbonyl in presence of Z and Hg and HCl. This is basically Clemmensen reduction. Okay, I will not take any risk. I guess it is clear. Okay, very good. Let's go ahead. Your favorite problem. Look at this. A champion. They are very good with the. I was confused about the Clemmensen, if it is single M or if it is double M. Fine. That's why I wrote only CR. Anyway, let's go ahead with this problem. Yes, let's give it a try because it is taken from a model paper. Okay. So yeah. So basically, will the PDF be sent or yes, just after I will finish. If you have liked the session, if you have subscribed the channel, then only you will get the PDF. Okay. Okay, let's go ahead with the problem. First, you can see. Just a minute. Let me just have some water. It is a 5-marker problem, okay? It is a 5-marker problem. So, yeah, let's go ahead. The compound A has some molecular formula C7H8, okay? C7H8. Okay, so I can guess definitely it has some benzene ring. Because more than what I told you, more than 6 carbon, you can have an idea that it must have benzene ring, okay? Next, C7H8 is heated with alkaline KMnO4, okay? It's heated with alkaline KMnO4, strong oxidizing agent, right? Followed by acidification, okay? Followed by, this is number 1, number 2 is acidification, H+. Okay, strong oxidation, fine. I'm ending up with C7H6O2. This is my B. heated with reagent X, heated with reagent X to give me compound C. C has molecular formula 78 gram. Okay, I got it. So basically 78 gram means I must have benzene here. Okay, 78 gram is the weight of benzene. Okay, now backward I will go. So from where I will get up benzene? So you have to heat something with 2 oxygen. So definitely it's nothing but carboxylic acid. Benzoic acid I mean to say. So with what you have to heat? Decarboxylating reagent. NaOH plus CaO. Okay, you have to heat it with soda lime. Right? Okay, now this benzene, I mean this benzoic acid came from what? Came from this toluene, strong oxidation. Right? I guess this is clear now. It's very easy actually. Write the structure of compound A, B and C. We are done with it. Right? Next. Okay, very good distortion. Next. Okay, it's a continuation. Identify X and mention its role in the reaction. So X is what? X is basically decarboxylating reagent. Decarboxylating reagent. Okay, so what is this is the role. The reagent is NaOH plus CaO, soda lime. Right? Let's go ahead. Okay, so again one that type you can see. Provide the general reaction to prepare a haloform from methyl ketone. That already I did haloform. I guess you can do it RCOCH3 you can write in presence of I2 plus NaOH. Okay, I2 or X2 you can write. General formula they asked, better you go with X2. Better you go with X2. X2. Okay, so you will end up with RCOO minus and you will end up with CHX3. Okay, this is the general reaction. Okay, one more part, sorry. In a given chemical reaction, write the structure and name the compound Z. Okay, name a reagent which is used to detect the presence of alpha methyl group in a carbonyl carbon. So definitely the same thing here. Alpha methyl group means this one. This is called alpha methyl group. So the reagent that we use is NaOI. Okay, sodium hypoiodide, or that is coming from I2 in presence of NaOH. I2 in presence of NaOH. Okay, so now in a given reaction, write the structure and name of Z. Z from where I'm getting. So if I just treat this, detect the presence of alpha methyl group in a carbonyl compound. So definitely you will end up with this acid, I mean this carboxylate plus iodide. That's it. Or bromoform. Okay, I guess this is clear. 2,4-DNP. 2,4-DNP why? General organic haloform. Haloform methyl ketone, name a reagent which is used to detect the presence of alpha methyl group in a carbonyl carbon. Name in a given chemical reaction, write the structure and name the compound Z. What is Z? Z, I guess this is coming from some other question. I have not done one reaction for B. What is B? That is not the continuation. Provide the general reaction. Where you are getting B, bhai? Alpha methyl group is there, fine. Write the structure and the name of the compound Z. Where is Z? I guess something I have missed here. Anyway, we will recheck the question and again in the evening I will put it. Okay, don't worry. I guess I missed something here. Next, okay, write the steps involved in the mechanism of acid catalyzed dehydration of ethanol to ethene. That I guess I told you already. Okay, for this case, this particular reaction also I told you. Let me just write it once again. This is that acid catalyzed reaction. Next, let me just write this. This is, you are going to get benzoquinone, double bond O, double bond O. Here you will end up with 3 bromo. Here bromine, here bromine, here bromine. Okay, I guess this is clear. Let's go ahead. Okay, so we can start the biomolecules. Okay, biomolecules will hardly take 15 to 20 minutes. Okay, so let's go. So yes, what is reducing sugar? These are the definition based question. Carbohydrate which can reduce the Felix and tollens. Okay, give one example of it. Okay, next, what are the non-reducing sugar? The carbohydrate which does not reduce the Felix and tollens. Give one example, that is sucrose. Next, give 2 methods to preparation of glucose. First you can start from the cane sugar, next from the starch. So hydrolysis of the cane sugar can give you the what it calls in alcoholic medium, definitely we can give you the glucose and fructose in equal amounts, and from the starch also in presence of H2SO4, if you just boil this, you will end up with the n amounts of glucose. Okay, let's go ahead. Here comes very important questions. Okay, how does glucose react with hydrogen iodide, or how do you show that glucose contains 6 carbon atoms in a straight chain? So basically, if you have glucose, if you treat this with HI in presence of red phosphorus, that will give you a N-hexane. That will tell you, yes, my glucose is having 6 carbon chain. Very important question. Okay, next, how does glucose react with the hydroxylamine? Here you can see it will form the glucose oxime. That will tell you that it contains 1 carbonyl carbon. Okay, next, I guess this is clear. Next, how does glucose react with acetic anhydride? So basically it shows that I am having 5 OH group in the glucose itself. Okay, the pentaacetate form. Okay, next, how does glucose react with bromine water? It will give you the gluconic acid. Okay, gluconic acid will tell you that I am having the aldehyde group present in it. The carbonyl that you got in hydroxylamine reaction, that carbonyl is none other than an aldehyde. Okay, let's go ahead. How do you show the presence of alcoholic group in glucose? So basically we can just oxidize it. We can oxidize glucose, or we can oxidize the gluconic acid. We will end up with the saccharic acid. Okay, so saccharic acid will tell me that yes, whatever the OH group I am having, they are attached in different carbon. Okay, they are all primary alcohol. Okay, next, write the open chain structure for the Emil Fischer structure of glucose. Okay, so this is the Emil Fischer structure of glucose, open chain structure. Okay, let's go ahead. Give the limitation of open chain structure. So as you know, though it contains 1 aldehyde group, it doesn't react with NaHSO3. It has no clarification about the anomers, alpha and beta forms, right? Another one is pentacetyl glucose does not react with hydroxylamine, right? It says that maybe free aldehyde group is absent. Okay, so these are the limitation. Okay, let's go. What are epimers and anomers? Super important question. Let's go ahead. What is epimers? Sugars with which differ in their position at the carbon. Okay, but if you see the sugar which differ in their configuration at C1, okay, that is anomers. I guess this is clear. Let's go ahead. Okay, so this is basically Howard structure of the glucose, and so Howard structure of write the Howard structure of alpha D glucose and beta D glucopyranose. Alpha D glucose and beta D glucopyranose. Okay, so alpha and beta, I guess I don't have to tell you. Alpha, what happens? The OH comes below, and in beta OH comes up. Okay, so I guess this is clear for you. This is how you have to draw the structure. Next, very important, Howard structure of maltose. So this is how you have to Draw the structure alpha D glucose and alpha D glucose in the carbon 1 position, join them with the glycosidic linkage. Okay, next mention the type of glycosidic linkage in the maltose, that is carbon 1 and carbon 4. Okay, so here you can see carbon 1 of the glucose linked with carbon 4 of the another bit alpha D glucose. Okay, given reason maltose is a reducing disaccharide. Sorry. So it is a disaccharide because it has a free aldehyde group that can be produced at C1. Okay, so here in this particular case, in this carbon 1, sorry, here in carbon 1 you can produce a free aldehyde unit, okay, that can reduce the Fellings and Tollens reagent. Okay, let's go ahead. What you are saying? Which structure is important? Maltose structure is important, my dear. Okay, lactose is also important. I am showing you the important structures. Okay, you see, lactose is also important. Maltose and lactose you practice. Okay, so this is the structure of lactose, that is beta D galactose and beta D glucose. Okay, type of glycosidic linkage, carbon 1 of beta D galactose and carbon 4 of beta D glucose. Okay, so give reason lactose is a reducing disaccharide. Again you can see in the carbon 1. Okay, so you can, there is a possibility to form the aldehyde unit. I guess it is clear. Let's go ahead. 3 model paper, 3 practice paper, 2 preparatory paper, solve. I'm not getting your point what you are saying. Yes, if you have practiced enough you will do good, don't worry. Let's go ahead. Name the storage polysaccharide present in animals. So I guess you know this, glycogen. Where it is found? It is found majorly in the liver, muscles and brain. Next, give any 2 difference between starch and cellulose. I guess the answer is not visible, right? Oh, I don't know how to zoom. Anyway, starch and cellulose, if you see, made up of, starch is made up of alpha D glucose and cellulose is made up of beta D glucose. So once you will get the PDF, you will see the answer, don't worry. Okay, next, in starch you will end up with the glycosidic linkage, okay, alpha glycosidic linkage, and in cellulose you will end up with beta. Okay, and starch is linear, cellulose is starch is branched and linear, but cellulose is always linear. Let's go ahead. What are essential amino acid? Alpha amino acid. Give one example. Here you can see they cannot be synthesized in the body. Lysine, valine, leucine, this type of example you can give. Okay, next, non-essential, they can be synthesized. Okay, example glycine, alanine you can give. Next, zwitter ion or dipolar ion. So that is basically it's one of the form of amino acid. So as NH2 unit is basically basic and COH unit is acidic, so they form the dipolar. Okay, so how does it looks like? Let's say I am having this. COH and NH2, right? So CO minus, and here it will form NH3 plus. Okay, so this is called zwitter ion. One example you give. Okay, next, how are proteins classified based on the structure or molecular shape? So definitely first fibrous and globular, right? This is a very important question, my dear. Fibrous protein means, just write some characteristics. They are insoluble in water, fiber-like appearance. They are basically polypeptide chain parallel, held by hydrogen bonding or disulfide linkage. Example, keratin, muscle fiber, this thing. Globular protein, if you see, they are spherical in shape, soluble in water. Okay, insulin, albumin, hemoglobin, these are the examples. Let's go ahead. What are denaturation of protein? Which level of structure remain intact during the denaturation of globular protein? Okay, so this is basically the loss of biological activity of the protein by the pH change, by the heat. Okay, this is called denaturation of protein, and 1 degree structure, 1 degree protein, they becomes intact. Okay, let's go ahead. Explain the classification of vitamins. So fat soluble and water soluble, you can give it like soluble in fats and oil, A, D, E, K, and water soluble, they are vitamin B and C. Okay, let's go ahead. So here comes all the vitamins. I told you multiple times. Once again, vitamin A, if you are having it, the source is fish liver oil, carrots, butter, milk, and in absence or in deficiency of it can make you face xerophthalmia, night blindness, etc. Vitamin B, that is the name, chemical name also sometimes comes. This is called thiamine. Source you can see. In absence, you can get beriberi. Okay. Vitamin B2, that is basically different type of digestive disorder, burning skin, etc. Okay. Next, vitamin B6, pyridoxine, convulsion you can get out of it. Okay. Vitamin B12, source you can see, and you will see that anemia. Okay. Vitamin C, that is ascorbic acid, this is the source, you already know, you will face scurvy out of it. Vitamin D, exposure to sunlight, deficiency can give you ricket, okay, or osteomalcia. Next, give difference between DNA and RNA. So this is basically the DNA RNA. So first you can write about the strand. So DNA is basically double stranded, RNA is basically single stranded. Sugar you can mention, this is basically deoxyribose sugar, deoxyribose sugar, and for RNA it is basically the ribose sugar. Okay, nitrogen base that you can write A, adenine, guanine, cytosine, thiamine. For this case, adenine, guanine, cytosine, and uracil. Okay, these are the differences. Let's go ahead. Okay, so now here you can see hormones. So hormones, the question basically, the basic question, the types, examples, like you can see polypeptides, they can ask you like give one example, that is amino acid derivatives. So you have to tell epinephrine, norepinephrine, thyroxine. Give one example of steroidal hormones, that is estrogen and androgen, like that they can ask. Okay, so let's go. Some hormones and function overall I will tell you here. Wait, I guess these are written in black, that's why. I will change the color of this slide and it will be clear, okay? Don't worry. Okay, so here you can see Howard structure of sucrose. So this is basically alpha D glucose and beta D fructose, okay? Glycosidic linkage in between this, but like I feel lactose and maltose are more important for your this examination, okay? Next, give reason. Sucrose is a non-reducing sugar. It's an important question. Mention the glycosidic linkage in sucrose and why it is, like what is invert sugar, that is also important. What is glycosidic bond? Okay, invert sugar, this particular question is very important. So here you can see reducing group of glucose and fructose are involved in glycosidic bond, right? See, these particular 1 and 2, this particular portion, these two particular portion can form the free aldehyde. They are involved in glycosidic bond. That's the reason sucrose is non-reducing. Okay. Next, question C. Glycosidic linkage in sucrose, that is carbon 1 of alpha D glucose, carbon 2 in beta D glucose. Okay. Next, what is invert sugar? Invert sugar, it's a very important question. Basically, sucrose is dextrorotatory, right? But after hydrolysis, it gives dextrorotatory glucose and levorotatory fructose. So levorotation of the fructose is more than that of the dextrorotation. So as a result of this, overall rotation comes up to be levorotation. So we are starting with a dextrorotatory sucrose and the upcoming solution is becoming levorotation. Okay, that's the reason, because of the change in rotation we are calling it invert sugar. Okay, I guess this is clear to you. Okay, what is glycosidic bond? Glycosidic bond, this is basically two monosaccharide. They are joined together by an oxide linkage. By the how it is formed? By the removal of 1 unit of water. Okay, so I guess it is clear, no doubt. All are theoretical questions only. Okay. So here you can see, name the storage polysaccharide present in plant, name the monomer present in the starch. Okay, storage polysaccharide in plant is basically starch. Monomer unit present over there, that is basically, what is the monomer unit? So that is basically alpha D glucose, right? Alpha D glucose is the monomer unit. Component of starch, amylose and amylopectin. Write two differences of amylose and amylopectin. You can write about the structure, like 15 to 20, one case 15 to 20% starch, another case 80 to 85% starch. One case it is soluble in water, another case it is insoluble in water. Okay, like this type of thing you can go ahead with. Okay, let's proceed. Okay, wait. So these are the most important topic. I guess it's not visible properly, I'm telling you. So carbohydrate, the entire functional analysis of the carbohydrate, it's important. Okay, the reactions, like the reaction with hydroxylamine, HI, okay, acetic anhydride, these things are super important. Proteins, reducing, non-reducing sugar, peptide bond formation, zwitter ion, essential, non-essential amino acid, protein structure is important. About vitamins, important thing is fat and water soluble vitamin, deficiency diseases, their function, RNA, DNA differences, nucleic acid, and a little bit structure. Okay, Haworth projection. Okay, Haworth projection of maltose, lactose, sucrose. These three you practice properly. Okay, I guess this is clear for you. So yeah, this is the end of the session. So yeah guys, we are finally done. So yes, again you have some time. I will start again in the session in the evening. Just in 1 hour I will just cover up the entire thing. Okay, just to give you what is the important thing, last minute revision, I will just tell you some suggestion and all. Okay, so yes, if you really appreciate the effort that I am giving, I always appreciate my student. I also need some appreciation and motivation from your end as well. So please give one like. If you have not subscribed, please subscribe this in order to get the PDF. Otherwise, no PDF, nothing. Okay, so yeah, thank you so much. Thank you for watching till end. Yes, bye all of you.